I'm Maurice Naftalin. This is
Kirk, Pepperdine.
Yeah, and the hashtag that we're using for the talk today is Java 8 Fairies. We had a real struggle to think of a hashtag that was going to be short enough for, like, good and wicked fairies. Probably seemed like it was going to be a bit long. So Java 8 Fairies is us. Okay, some introductions.
Okay, so this is, well, as many of you probably already know, I do a lot of performance tuning, and I speak about performance tuning. And a couple of years ago, with some guys in London, we co-founded Clarity, which is really just a company about performance diagnostic tooling, and some other things. And generally, what I say here is, use Google if you want to learn more. And we have, where are we? A puzzle, right? So I know some of the guys down the front here, you're not eligible, but Maurice has graciously decided to give away one of his Mastering Lambda Java Programming in a Multi-Core World. I have to tell you, this is a really good book, and I actually paid for it. And you didn't even sign it. Good. I didn't get a copy, and you didn't even sign it. Okay, so pop quiz. What's this? Does anyone know what that is? So Pierre says it's a chip. Very good, Pierre. This is for a copy of this very excellent book here. It's a microprocessor. Fantastic. We're narrowing it down. So I guess if you get it as a group, I'll have to give each one a page. Looks like a, oh, yeah, could be. Any ideas? I don't know. No one's even looked at, tried to use Google yet. Is the Wi-Fi not working? Smart card, Java smart card. No, even older than that. Is it, sorry? Z80. Z80, even older than that. Intel's first chip. That's Intel's first microprocessor. I mean, we'll show you some other diagrams later on, but just to give you an idea, like what this thing is, it's a 4-bit address, 4-bit processor. The entire documentation for the chip is found on like 120. Well, it's about a 20-page leaflet, right? I mean, if you compare that to chips today, here you are. He'll sign it afterwards, unlike my copy. So if you look at chips today, the diagnostic registers on the chip require, like, we read these things regularly, right? So they're 14 to 17,000 page documents, and so this is just the complexity that that we're dealing with today that we didn't have to deal with back then when they built this wonderful thing. So I mean, probably have a bonus. Do you know which pins are the address and which ones are the data? We'll leave that one going. Okay, Maurice.
Okay, so that's Kirk's introduction. Here's my introduction. I never know how to describe myself, so I use too many words. If you know about me at all, then it's probably through one of these two books. I'm the co-author of what I always never fail to call the very best book that was ever written on Java generics, and I'm the author of a book which I can't say the same about, to do with lambdas, but I think it's okay. I'm also a member of these. I'm a member of these community schemes as well. The Java Champions and I'm a Java 1 rockstar. I also maintain the Lambda FAQ, which was the thing that kicked off the book, now a bit dusty through lack of maintenance for the book. And here, Kirk has insisted that I should tell you about the first computer I used. I don't know, it's a kind of history session today. So this was actually a pretty great computer. It was there's a Varian 620i. It was pretty fast. 1.8 microseconds, and it had a lot of memory, 4,000 words. Well, that's the one that we had. It was an embedded computer. Oh, it was pretty good. I played the first ever computer game I ever played on that. It's a long time ago. on living history. Okay, the agenda for today is this. We're going to look at the things that you do when, essentially, we're going to go through something like a performance tuning exercise, really. We're going to define a problem. The problem's kind of interesting and takes a bit of motivating, because we're really interested in stream performance, and so we're going to solve this what looks like really simple problem in what looks like a rather complicated way, because this is the way you have to do it with streams. We're going to implement a solution. We're going to analyze the performance of the solution. We're going to do some things that people who teach performance tuning do to persuade you that you probably don't want to jump to the first possible conclusion that you should have. So you find a bottleneck, and the process of performance tuning is when you find a bottleneck, you re-implement the solution, you correct whatever the problem was, and then you analyze the performance again, and so on. So there's a cycle there, and we're going to go through that about 4 or 5 times this morning. Time permitting, and that's really going to take us to the end of. On the way, we hope to illuminate both how streams work and how you should look at performance problems. Is that fair? And finally, we've got a section on fork-join parallelism what I've called fork-join parallelism in the real world, because up until then, we're looking at fork-join parallelism, the kind that the parallel streams manage. We're looking at that pretty much in isolation. We're sort of pretending that we have the machine all to ourselves. And so there's some extra things that we need to think about, because in the real world, that often isn't exactly the case. Okay, so here we go. Here's the case study. The case study is one that I came across when I was writing the book. What I wanted to do was to see how we could use stream code in a functional style to implement all the different options of grep. And it was just just for fun, really. And most of the options of grep are really easy to implement using stream code. But I came across this one, which I'd never heard of, and I don't know whether other people have. Grep minus b. And grep minus b displays the offset in bytes of a matched pattern in front of the matched line. So if you had a piece of code like this, a piece of text like this, which is taken from the Rubaiyat of Omar Khayyam, then the result of doing of running grep minus b on it would be this code. So I'm searching for a pattern which is uppercase W followed by anything followed by T, and that matches 2 lines. It matches the second line and the 4th line, and the second line begins at a byte displacement of 44 because the first line has 44 bytes in it, and the 4th line begins at a byte displacement of 122 because the first 3 lines have 122 bytes in it. So this is a problem, and you think this is a really easy problem, because obviously there's a kind of obvious iterative solution. There's also a little subtext here, text about the text, because I chose this text for a particular reason. It's a great poem, the Rubaiyat. The moving finger writes, and having writ moves on, nor all thy piety nor wit shall bring it back to cancel half a line, nor all thy words wash out nor all thy tears wash out a word of it. So Omar Khayyam was a genius. He was this 11th century Persian mathematician who also was a philosopher and a poet and a mineralogist and a geographer, and he wrote treatises about music and Islamic theology and all this kind of thing. And in his spare time, clearly, he was thinking about computing science because he obviously knew a lot about immutability.
I don't get it.
You don't get it, do you?
No.
Nobody ever gets it.
He was thinking about immutability. Okay.
Nothing ever changes, you see. So,
when did you put that in? Yeah.
Right, okay. It never goes down well, but I like it, so I'm going to keep on telling it.
Okay.
So there's an obvious iterative solution to this. There's an obvious iterative solution to this problem, which is kind of you process the file line by line, and you accumulate the byte displacement you've got so far into an accumulator variable. And when you get a match, you print the match out, and you also print out the displacement that you've got so far. It just couldn't be easier. It's like it's the first.
Just like you see up there.
Yeah, just like you don't see it there. Sorry about that. Thank you. So this is the problem that you set somebody in their kind of first week of programming. But we can't do that. We can't choose that obvious solution if we're going to use streams, because we're in the functional style here, and for very good reasons, there are no accumulators that are going to be allowed. The reason there's no accumulators allowed at root is that we're writing code as though it was at some point in the future going to be executed in parallel. And if we have accumulator variables, then different threads doing their part of the work are all going to have to use the same accumulator variable, and therefore there's going to be contention on it. So if you don't protect it with mutual exclusion, it'll be corrupted, and if you do, you'll have a hot lock, and you'll actually lose parallelism. So we have to find a non-accumulator type solution for this. So to take a step back, and I have to do this, I have to add a bit more background in here now, is I have to tell you something about streams and how they work, so as you can see where I'm going with this. So I'll apologize, because I know for a lot of people, Java 8 streams are now routine, but in different audiences, when I ask how many people are using Java 8 streams in their work,
why don't we ask that question?
I get wildly different answers. Kirk's saying something a bit radical here. How many people are using Java 8 streams in their daily work?
Whoa.
So it's about 50%.
That's pretty good, actually.
Yeah, okay. So I'm going to beg the patience of the people who are using them, and also I'm going to beg the patience of the people who aren't using them, because it's going to be far from a thorough introduction. What's the idea of streams? We want to replace loops for aggregate operations. That's the big deal. So instead of writing code like the code that you see on the screen here, which you can kind of work your way through, it's pretty straightforward. We've got a list of person objects, and each person object has an attribute of a city. And what we want to do is we want to accumulate the names of all the cities, which are all the cities inhabited cities that have less than 4 characters in their name. And so we're iterating over the person objects, and then we're getting the city for each person object, and then we're testing to see if the name is less than 4 characters, and if it is, we're dumping it into a new set. And this is pretty characteristic in miniature of the way that we do lots and lots and lots of bulk processing in Java nowadays. And we're going to do something different, really radically different with streams. The stream equivalent of that looks something like this. And assuming that we've still got the same collection, a list of person, that's people. Now what we're going to do is we're going to put we're going to stream those values, and that means something I'm going to explain some more in a moment. But the idea is we're going to put them into a dynamic data structure, and the values will be processed by the operations that follow. So each value will be mapped to each person value will be mapped to the city that person lives in with the map operation, and then there'll now be a stream of city objects will result, and each one of those city objects will be filtered to ensure that it satisfies the predicate there. The predicate says, for each city, test to see if the length of its name is less than 4. If it is, then it passes, and if it isn't, then it fails. And then at the end, they're going to be collected, and this is really important for what we're going to be doing. They're going to be collected into a set. The framework decides what kind of set it's going to be. At the moment, the implementation collects them into a hash set, but that's not guaranteed in the future. So the claim is that this code is more concise, more readable. The operations that make it up are more easily composable, and crucially for us, it's parallelizable. So in order for you to run this code in parallel, we'll come back to this more later on. I'm not going to talk about this straight away, but it's important to have in your mind that you can replace stream as the stream method of the person list with a parallel stream, and that means that the operations are going to be executed in parallel. We'll look at that in a lot more detail in a bit. So I'm still working towards the idea of how am I going to implement this grep -b in a functional style without using an accumulator. Let's go on and take a look at what streams look like when they execute. This may seem like a kind of rather kind of elementary animation to you, but as the talk goes on, I hope you'll see the value of it. So we're imagining we've got a source. In this case, I've just said it's a source of, I'm imagining it's an array with 4 values in it, typically, obviously, a lot more than that. And I'm going to put them through a map filter, and then through a map operation, that's an intermediate operation from which a stream results, and then a filter, which is another intermediate operation from which a stream results, and they end up in some kind of reduction. And I'm not saying at this point what kind of reduction, but a reduction is something which just kind of takes all the values that have come down the stream and somehow collects them together into a single value. So reductions might be, for example, adding up all the numbers that come down the stream, or it might be taking all the values, all the elements that come downstream and putting them in a collection. Those are two different kinds. There's a third kind, for example, which concatenates all string values that come down a stream and puts them into a single string. So the basic idea is a reduction collects them all together. So here comes the first element, and it's mapped from x0 to y0. It passes the filter, and it goes into the reduction. And here comes the second one, and it maps x1 to y1, but it doesn't pass the filter. And the third one, similarly, it maps to a new value, passes the filter, goes into the reduction. So this is the idea. And you'll see that something important about this is two important things. One of them is that each value is processed by all the intermediate operations in one go. So it's quite unlike the idea of bulk processing using iteration over collections, where typically what you do is you do all the operations on a collection. You do a single operation on a collection, and then dump the result into a new collection, and then do a single operation on all the values in the new collection, and so on. Here we're doing all the operations on each value in turn.
So what you're saying is that all of these operations sort of get fused together then?
They're fused together, and actually that results in big optimizations, or
right.
sometimes potentially results in big optimizations in the way that they're performed.
Okay.
The second thing to notice about this, though it doesn't really come out in the diagram here, but if you don't have a terminal operation, as I've got here, then the stream can be set up, but no values will actually pass down it. So you want to think of the terminal operation as being the thing that pulls values down the stream from the source, and it's only when the terminal operation is called that the values start to flow. So here's a diagram. I'm going to focus quite a lot on collectors today. I'm really keen on these terminal operations. One of the very clever things that the Stream API does, one of the best things that it does, is there's a sub-API, a smaller API of it, which has this really useful function of taking values that come down the stream and putting them into different kinds of collections, joining them together in various ways. And the thing that makes this really neat is that it will use standard collections, the kind of the Java collections framework, 1.2 collections like hash map and hash set and array list. Even though these aren't thread safe, it will take values that have been computed in parallel and manage thread safe dumping into them, accumulation into them. So here's a diagram. Here's a very simple diagram of one of the collectors. Mostly, you don't have to write your own collectors. There's a static class called, in fact, collectors. And the class is called collectors. It's a utility class, and it's got loads of static factory methods on it, which will give you back collectors to do particular things. One of them, for example, is toSet. So you see, what I'm doing here is I'm taking the stream of people, and I'm just collecting them into the collector that is returned by collectors.toSet. And this is a really simple idea. It's kind of insultingly simple, really. I'm astonished everyone's still here. Here comes Bill. We've got three persons in the three-person objects coming down this stream, and the collector creates a set internally, and each one of the values that comes, the elements that comes down, get put into the set, and at the end of when the stream is exhausted, as we say, because there's no more values left in the source, then at that point the collector emits the kind of collection that it's intended to do. So in this case, it's a set containing John, Bill, and Amy. So this looks like a really straightforward idea. There's a lot more to say about collectors because it's a lovely API. It's really great. One of the best things about it is that it composes very nicely, and so you can actually build really sophisticated queries on your data very, very neatly in the sort of Unix tool building type of style. So I've said that one of generally speaking, terminal operations are about collecting things together. functional programmers have been doing this for a really long time. They've been taking values that come down, not come down streams as we're talking about here, but they know how to take values and to put them together. The classic example of how to do this is something like addition. So if you, the point here is we're trying to avoid having an accumulator. How would you take all these values, say in this case, int values that were coming down a stream, and add them together without having to keep a running total of them? Because if you keep a running total, then you're giving up any possibility of parallelism. So the classic way of doing that is with a reduction, and the idea is you define an operator, in this case the addition operator, and I've chosen the one here with an identity. The identity is 0, because if you add 0 to anything, then you just get the same thing back. And now you can see, supposing you've got a whole lot of values in an array, but this is just a convenient way of thinking about a whole series of values. You could combine them using this symmetric addition operator, and you can see that you don't have to keep a running total anywhere. In fact, there is a running total on each side. You could imagine the expression tree on the right-hand side and the expression tree on the left-hand side both imply that the accumulation is taking place in a single variable. But you can see at the bottom, where they're combined, that actually that's not necessary. I mean, in other versions of this talk, I sometimes just show different expression trees with a different order of evaluation in the two halves there to show that really there's no necessity of using reduction eliminates the necessity of having an accumulator variable. The way you'd write this code, if you were going to do it in the stream API, would be like this. I mean, luckily, you don't actually have to do this. But if we had an int stream and we wanted to add all the values in it, then we would say the identity that we want to use is 0, and the combiner, the binary operator that we want, takes two values, an A and a B, and returns A plus B. Okay. Luckily, you don't have to do this because there's a convenience operation, a convenience terminal operation called sum that saves you from having to write this. But that's exactly what it does behind the scenes. So the question that the designers of the Stream API faced was, can we do the same kind of thing if we want to do what people characteristically do in Java, which is take things out of collections, process them, and dump them into new collections. And so the idea was, that, and they actually did have this idea for quite a long time, was that you could do something of the same kind if you just replaced the identity with an empty collection, right? So you would have, you could have an empty collection, you could have an accumulator down these long left-hand sides here, and then you could have a combiner to put them together. So it'd be something like, the empty, say it would be an empty array list, and then you could say, well, I'm going to successively add elements to this array list, and then I'm going to use add all to combine two array lists. Well, that doesn't work because the idea of reduction is that the identity is really going to be fixed. It's going to be immutable. So actually what they had instead, what they introduced instead, was something called mutable reduction. And this is how the collectors work behind the scenes. You don't usually have to know about this, but it's quite good background. And what they have, instead of having an identity, is they have a supplier. So the supplier is a lambda, a function which takes nothing and returns a new one. So each time you call it, you're going to get a new empty collection. And now what's happening is we have exactly the same kind of pattern as we had before, but we have a new empty collection is created, and then each element in turn can be added to it. But when we have to combine two collections, we need a combiner as well. So now we need 3 functions for to write a collector, and that's the supplier, an accumulator, and a combiner. In the case of array list, it would be a new the parameterless constructor for array list. It would be the add method of array list for the accumulator, and it would be add all for the combiner. So that's the background that I needed in order to tell you how we're going to solve the problem of doing grep minus b with streams. So here comes the solution, which is in the form of a collector. And obviously, when we've implemented the solution, we're going to get on to analysing the performance and seeing whether it works and how well it works. So the idea of it's quite difficult to think of a functional solution for this stuff to begin with, and then when you see it, it's completely obvious. So the idea is we want to end up with some kind of linear data structure, which is going to contain all the lines of the text, and it's kind of quite clear that it's easy to have within this linear data structure, each element could obviously contain the length of each line. That's not a problem because you can find that out very easily. But the question is, how are we going to... I've left a field blank here because what I want in that is the cumulative displacement. So if I could see how to make this thing, then I could see how to solve the problem. Because then now if I process this linear data structure using pattern matching, I've got the displacement of each of the I've got the displacement of each element already in there. So, the key to finding the answer to a problem like this is always, I think, to look for a partial solution. If you can imagine how you could combine two partial solutions together, then all you have to do is imagine how you're going to create an initial partial solution, and you're done. So the two partial solutions would look like this, and you can see that the key thing here is that each partial solution is correct in itself. So the left-hand side contains the initial, the first two lines, and each one of them has its length, but each one also has its total displacement. The first line is the moving finger rights, and its displacement is 0. But the second one has a displacement of 44, because that was the length of the first one. And on the right-hand side, we've got the same situation. So the total displacement of the third line is 0, because it's the start of a partial solution. And obviously the total displacement of the last line is, in this case, it's 42, because that's the length of the third line. So you can see, I think, how we would combine those together. Here's a diagrammatic way of doing it. Basically, all we need to do is just add the displacement of the last line of the first half to the length of the last line of the first half. That gives you 80 in this case, and that's how much we need to push forward the displacements on the right-hand side, and that now allows you to, and that now gives you the total. So this is the basis of the solution. It's really not, once you see it, it's really kind of a bit trivial. The overall solution now is going to look something like this. This is how the combiner will look. This is how the combiner would look if you were starting from single element partial solutions. But in fact, you're not going to do that. What you're going to do is you're going to have the accumulator create these partial solutions. This is what the overall picture looks like now. You've got the supplier produces a new empty data structure, and the accumulator will take each one of these, will take a line of text and put it into the existing collection in a rather obvious way. So it adds one of these data structures here, and it fills out the fields in, I think, fairly obvious ways. So that's the basis of the solution. We've got a supplier, which is just a new. In fact, the implementation doesn't use an array list, but it uses a deck, because that gives a better performance when you're adding things onto the end of it. Well, it gives better performance. So we've got a supplier which creates a new deck. We've got an accumulator which works in the way that I've shown on here, and we've got the combiner which works in the way that I showed on the last slide. And so now we are ready to analyze the performance. Kirk, where are you? Shall we analyze the performance?
Well, that means you need to have a demo, right?
Well, does it?
Well, do you have performance targets?
How would I? That's really the question. You've spoiled the repartee here. How do we know whether we've got a problem?
Well, because you're not meeting your performance targets. If you don't have any performance targets,
right? So we don't.
It's not important.
So we don't need to.
I think this is a big message that Brian gets. Tries to push across that.
Yeah,
without any performance targets, there's no point, right?
Right.
So, in this case, do we have performance targets?
We're going to pretend we have performance targets.
I think we're going to say this is infrastructure code. It's probably, we need to make it.
I think we need to pretend that we've got performance targets. We will do that. We wanted to make the point that that the performance tuning exercise isn't any use to you if you don't know where you're going with it. Because if you don't have performance targets, then you have no way of knowing whether or not your code is running fast enough. It's no good to say it's too slow if you don't know what too slow means or what fast enough would mean, because you're going down a never-ending road if you're trying to optimize until everybody thinks it's fast enough. So performance targets, non-functional requirements, should be as important a part of your specification as functional requirements. But let's pretend that we do have performance targets. So what else might be the problem? These slides are headed, why shouldn't we optimize?
Why should you not optimize?
Why shouldn't we optimize code? Well, there's another possibility. Another possibility is that we do have a problem,
but it's not in our process.
But it's not in our process.
And that's a problem that we see very commonly. As a matter of fact, the last 2 performance engagements I was engaged in, people say, why is my application slow? And you look at it and say, no, your application isn't slow. There's no problem here. There's something external in the environment that's actually causing some difficulties here, or there's a problem with the feeders into the system. So maybe you're drip feeding the application, so you just can't prove performance, or you just can't get the performance that you're expecting out of your application simply because the environment won't let you. This gets to be a bigger problem in virtualization. It gets to be a really big problem when you try to do demos at talks, because you're running Keynote and I don't know how many IDs you have here and how many cloud services you have running and all of this other stuff, right? So, you know, which begs the point. I mean, when we are going to run experiments or benchmarks, and we want to run it in a controlled environment, and part of the controlling the environment is making sure that all of these things that are going to generate noise in the environment are actually turned off. So you can actually see what the performance is. So when you do get it into a noisy environment, you can recognize what's noise and what's not. Okay, what do we have here?
Well, we've got some code. I'm going to run it on that little. Oh, I should probably put this on.
Right. So we need to know if your system is quiet, right? Or do you want to explain the code?
Well, let's just run it and see what happens, shall we?
No.
You don't want to do that?
No.
Okay, right. Let's see let's see if the system is quiet then.
Let's see if the system is quiet. So so what are we going to do? We have a little CPU.
We do have a little CPU thing if I can find it.
Okay, let's take a look at the CPU here.
I've got a lot of problems with desktops here. Okay, so.
Okay. Right, so it's a Mac, but we can use this. So we can look at CPU load there, and it's like, ugh. What happened here?
It seems to be calming down a bit now. Wouldn't you say?
Yeah. Okay. I think CPU-wise we're okay. I mean, next thing you want to check is how much memory we have, because, you know, the one thing we don't want is the JVM swapping. That will cause problems. And yeah, okay. So it looks like you have enough left over. We can do this. Right.
Okay. Should we do it then?
Yeah, we should do it.
Right. So we're going to run this. I'm going to run this on a big file. I ran it on the sample text and it worked, so I'm happy about that. Now I'm going to run it on a big file.
Okay.
Let's go and have a look at the at what's happening to the.
Well, and it never did really understand what the performance requirements were.
They were that it should perform better.
It should perform better. Okay. So is 5 minutes good enough? Okay.
What do you see when you're looking at this, Kirk?
Okay, so I'm looking at this chart, at the CPU chart, and what I'm looking at is the red bits and the green bits and the black bits, because the red bits, the green bits, and the black bits are all telling me something about what this application is actually doing. In particular, the red bits represent CPU time assigned to the kernel, the green bits represent CPU time assigned to the user process, and the black bits represent CPU time that hasn't been counted for one reason or another. In other words, it may or may not be idle time, but it's certainly not being counted. So when I look at this thing here, I'm looking at the amount of red. First off, we got 4 cores, and you can see that core 0 and core 2 are actually the ones being used. The intermediate ones are hyper-threaded. And there's not a lot of activity going on there. So
people may not know that what the hyperthreading means. They aren't real physical cores.
Yeah,
It's actually physically it's a 2-core machine.
Yeah, it's a 2-core machine, and it's hyper-threaded to 4 cores. So the operating system has now decided that it only needs to use the physical cores. It's not really using the hyper-threaded cores that much. And what's happening is that the little green bits is doing a lot of work here, and it's driving load onto the kernel. So the bottleneck in this application has to do with how this particular application is interacting with the kernel code, right? So what we need to do is figure out, okay, what's it doing? So do you want to build a profiler to do this, or do you want to use one?
We'll just take a look at the.
Well, let's build a profile. We'll call it the Maurice profiler.
Okay.
So go to IntelliJ.
Okay, right.
You're running IntelliJ.
I'm running IntelliJ. Yes.
Okay. And where's the flashlight thing or camera thing? So hit the camera thing over there.
Right,
see what this thing is
so
doing.
that gives me a thread dump.
Oh, thread dump. Excellent. Okay. So we've just taken a profiling sample here.
Right. Okay.
So it's a single sample.
Right.
And what do we have? Runnable. There's the main thread. Blah blah blah. At the bottom, you just scrolled.
Oh, main.
Right there.
Here we are. Main.
Main. Excellent.
Okay,
And it's saying file input read. Oh, okay, fantastic. Well, that's good news because that's a kernel interaction, right? So we have a thread dump that actually matches the CPU graph way over there. Okay, let's single sample. Let's do it again.
One?
Yeah.
Let's have a look.
See what we got here.
Right.
So this is the Maurice profiler.
Did it take another one there? It didn't take another one.
Didn't take another one?
No, I don't think so. Why is it not doing that?
I think it is.
Doing it. It's just identical then.
It's identical. Okay. So let's go to this, the not your process sequential, not your process 41 Java thing. Just click on that. It's appended at the bottom.
Ah, it's appended at the bottom. Oh, thank you very much. Right, okay, yes, here we are. Not your process Java 41. Keep going.
Yeah, okay.
Yeah.
So we're getting this many, all profilers are just basically samplers, and they just sample and tell you what's going on, just like this.
We're getting a certain consistency here.
All you need to do is count the samples and see what the sample counts are telling you, right? Put it into a histogram, and you're good. Okay.
So this is the line, and this is the line that's giving us the problem.
So what are you doing there?
What am I doing? I'm reading from a file.
Okay.
Right.
And
file reader. That seems reasonable, doesn't it? Let's go and have a look at this file reader.
And that's an input stream.
Oh shit.
Okay. Okay. So that's not buffered.
That wasn't very clever, was it?
No. I mean, if you're not buffering, that basically means that you're dropping the buffer on every read, right? And you're reading a character at a time.
I'm reading a character at a time, aren't I?
Okay, so you read one character, drop the buffer.
It's not really very surprising. There's a lot of kernel time going into that.
Okay, this seems like a rather easy problem to fix.
Right.
Okay, let's put a buffer around that and see what that does.
So, yeah, that's right. You wanted to do that, didn't you?
Okay.
Okay. Do you want to do that now?
Yep. Okay. Why not? So, really, in this whole exercise, what we want to try to do is we want to look at the red bit, the green bit, and the black bit. And we want to see what the ratios are between these bits and stuff like that to help us understand what it is that our application is trying to do. In this case, as we can see, the red bit is very strong. It's about, right now it's running almost equal to the amount of green. Generally for Java, my threshold is around 10%, roughly.
Yeah, that's what I'm headed for, I think.
Okay. So generally around 10%. If the kernel time starts rising above 10% of what the user time is, then I'm going to be concerned that the application is putting a lot of pressure or asking the kernel to be doing a lot of work. And so what I want to do is I want to go into the application with an idea that I'm looking for these application kernel interactions. Now the other bit that's interesting here is we have the black bit, right? And there's a lot of black bit. If we're trying to get performance out of the system, we don't really want black. We want to fill that up. But unfortunately, it's the pressure that the application is putting on the kernel is preventing the application from actually saturating the CPUs. And that's why we have a lot of black. So once we solve this problem, hopefully, we should see...
Should we try it again?
Less red, yeah. Less red and less black.
Don't know how good it's going to be, but we'll give it a go.
Did we actually run this before?
No, we didn't, no.
Okay.
No, this is just like you to decide.
Oh, but it's also serial, right?
Oh yeah, no, we're not at the end of the problem by any means.
Yeah, exactly. So serial. That it's serial. Oh, that worked much better, didn't it?
Certainly improved matters a bit, hasn't it?
And not only that, you can tell you got rid of the kernel problem because the application kernel interaction, because there's no red. It is single core, so I'd imagine that all of the green bits, if you add them up, will add up to a single core.
Right.
Saturation.
Right. So,
cool.
the lesson of the first iteration is don't assume that if you're getting poor performance, that it's necessarily a problem. In this case, it was a problem in our code, as it happened. I put a problem into. I created a problem in the code in order to show that the operating system could be struggling.
Oh, you're trying to tell me that was contrived to test me?
There are all kinds of reasons why the operating system could be contrived. It has to manage different kinds of hardware, memory, network. What's the operating system?
Well, it's all the I/O
what
stuff.
What are 4 things? The 4 things.
Well, there's generally 4 things that you're going to look for.
The processor, memory, network, and locks.
Locks, yeah. Anything that's going to cause a lot of context switching.
So it could be any of those things. In this case, obviously, I made it I/O in order to, as I say, in order to give Kirk an example to shine, an opportunity to shine. He's very good, and he finds everything straight away.
Thank you.
So supposing we solved that, supposing that isn't the problem, there could be another problem. The problem now could be in our process. If we use tools like vmstat and iostat, and we look at the system behavior and narrow the problem down to our application, in other words, the JVM, there could still be a problem in our process, but it might still not be in our code. How could that be? You wrote the slide. What uses process time that isn't our code?
The JVM.
But in the JVM, there's something else that uses CPU time?
Well, it's the JVM doing its work. So there's all kinds of moving bits inside the JVM that actually are responsible for doing different bits, and obviously they're going to use CPU to get that work done. So there's a lot of maintenance work done. There's a lot of things like garbage collection is an obvious problem in a lot of applications. So can we check the garbage collector?
Let's have a look at that. Okay, so we've got another code sample here called not your. How's it gone? Not your code. It's your process, but it's not your code. So
well, technically, it's your code.
Well, it sort of is your code, but I think we'll probably see. Really, it isn't much here. Oh, you fixed this in a way that I didn't want. So let me just. I'm going to need to just show everyone what's going on with not your code. Here we are. Here's the configuration, and basically the most important thing about it is I'm going to take a look at the garbage collection logs. Well, you always should take a look at your garbage collection logs. This shouldn't be a special setting, but it's going to be important for us to have it on this time. Okay, so let's run this not your code and take a look and see what the garbage collection logs have to tell us about what's happening. Was there something you wanted to see about this while the
Not in particular. For me, like garbage collection logging is something that I recommend everybody turns on because, again, like the CPU, it's telling you a lot about your application. And we can use that data to actually infer what your application is up to. And we can make really important, help us make decisions as to which direction we need to go in terms of tuning applications. I
quite like this because the kernel time, it's that spike on the right from this run, it's finished already. The kernel time was really low. Doesn't that mean we're getting a lot of work done?
Well, we are getting a lot of work done. The point is it useful work? In this case, we can see that we have relatively good saturation of the CPU. We could do better, but it's still not that bad. But the system time is fairly low, and so there's a little bit of read activity going on, but the rest of it looks pretty good. Okay, so let's look at the garbage collection log. To do that, we're going to use Sensum.
Sensum is Kirk's baby.
My tool. So maybe we can get rid of the CPU graph there.
Okay.
If you don't mind, and let's open it up.
Let me make sure this is the right one. Okay.
That's the right one. It's about right. Okay, good. So do you want to?
Right.
Fantastic. Okay.
What would you like?
So basically, what we did is, or what I've been doing is, for the last number of years, is just writing these garbage collection analysis tools, and we've been putting some analytics in the top bit so that we can look at the data and we can look for trends, patterns, and stuff, and the obvious things that we want to find. So eventually the plan is to get rid of the graphs, so we don't have to look at the graphs. We can just sort of look at the text here, and it can help us find a whole bunch of things that's going on. So the analytics are telling us that we have a high pause time. So let's go take a look at, see what that says. And it says we have like a 24 millisecond pause time. That doesn't seem too bad. Yeah. But the pause time itself looks like it's 44.68%. So can we look at the application throughput metric there? The application throughput is 55.3%. So that means that the workload here is being split.
Roughly equally.
Roughly equally between the garbage collector and the application. So let's go down and look at the...
Seems like a lot of garbage collection.
So let's look at the summary.
Okay.
Okay. So in the summary, it's like... Sorry, I still can't stop laughing at this one. You've had 183 young generational collections per second for 24 seconds. Yes, Pierre's laughing too.
I don't understand it. What happened?
Okay, let me give you a target frequency here. That'll help you put this into perspective. Generally, I don't like to see things running faster than about like a young gen collection. Maybe about once a second, but probably about once every 2 seconds.
This is a bit more than that.
Slightly. Right? So, yeah, this is collections per second as opposed to seconds per collection or whatever. So, yeah, okay. So, so that means that if young gen is filling up this quickly, our young gen isn't big enough. Right? Because, well, basically, our nursery is Eden, right?
Yeah.
And so if we're just allocating at a certain frequency, we're just going to fill it. You know, then that means our GC frequency is now tied to our allocation rate.
Yeah. All right. Allocation rate.
Okay.
Okay.
And the size of yikes. Okay. And the size of our young generational space here. Okay.
Okay.
So basically, when I'm looking at this, I'm looking at the average allocation rate. Eyeball is, yeah, it's
about 1,000.
You can eyeball it at 1,000. I would eyeball it about 800. But yeah, anyways, it doesn't matter. It's quite high. So if we want to get to a collection every 2 seconds, then basically we need to, well, we need to somehow deal with the peak. So probably we're looking at about a 2 gig Eden space.
Right.
Okay. So
should we have a look at how it actually is set up?
Let's go. Yeah. Okay. So let's go back and take a look at how it actually is set up.
Right. Edit configurations.
And you have
VM options.
Can you click over there? Oh, look at that. That's nice.
How did that happen?
So you've put in an M instead of a G, I think.
Oh, that wasn't great. And
well,
that survivor ratio looks a bit odd.
Yeah, the survivor ratio basically means you've wiped out those spaces, so they're not going to. That's not going to be a useful size for them. So the way the survivor space works is it's going to take the young generational size and it's going to divide it up into 10,000 spaces. It's going to give, 10,002 spaces, and it's going to give 10,000 of them to our nursery, and it's going to give 1 to to each of our 2 survivor spaces that we have.
I think this was just a terrible mistake.
I'm not sure how that got in there, but I would get rid of it.
No.
And I would probably change that that M to a G.
2G, you think?
2G, yeah, okay. Exactly. So probably somebody just made a typo there when they were putting that in.
That's right, and that 10,000 is definitely a typo.
Right, okay. So basically what we want to do in this whole benchmark is we want to try to take garbage collection out of the picture. Right? I want to know what the allocation rates are so that I can understand if my application is as memory efficient as it possibly can be. In this case, I would say that you have a little ways to go to make it a little bit more memory efficient, but that's okay.
Okay. Right.
But the other thing too is that we want to make sure that the garbage collector isn't really interfering with our benchmark results in the small, so we want to try to control it to wipe it out. I think probably 2 gigs is good enough. In some cases, I might just make Eden big enough so that I never run a garbage collection during the duration.
That would be good if you can manage it. That's probably not very realistic.
But I don't think we'll manage it on this particular machine with that allocation rate.
Well, I ran it again with those changes. Let's see.
Yeah, it's about twice as fast, right?
If I reload this, does that work?
Yeah, okay. So look at that. No more high pause times. Our application throughput looks fine. The log duration now is 24 seconds, 33 seconds. Just look at the summary here.
Okay, summary.
Summary, yeah. And if we look at it now, okay, so now we have no fulls and only 388 youngs. So that's still quite a high frequency, which means that we still need to make it bigger. So we could still do better, but really the gain we're going to get, right, if you look at the total pause time, is only about 200 milliseconds faster, plus the effects of all of the context switching that these 388 garbage collections would inflict on the benchmark. So we could do better, but we're probably close to good enough.
Okay.
There's another interesting thing here. One of the indicators, so you talked about interference from outside sources before, right? There's an indicator right here that you have an interference from an outside source. So this is an added bonus. This happened accidentally. So,
it's all accidental, actually.
Yeah, that's the nature of performance things, right? But if you look at it, see the high kernel time thing comes up in yellow?
Yeah.
Can we click on that analytic there?
So let's see what's going on there.
So let's see what it says there. So kernel times exceeded user times 4 times in this log file. That shouldn't happen. If you think about the garbage collector, the algorithm itself, right? It runs completely in user space. It does not run in kernel space. So we should not have seen that. This thing should have come up green. Now, what this thing is saying is that something caused the garbage collector threads to accumulate kernel time, which means that the kernel took a long time to process something, which means that something else was in the kernel actually preventing it from making forward progress. Can we go look at the, scroll down here? So just scroll down. Down, 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 down. And if you look at CPU summary. Yeah. Okay. So, so if we look at this, there's your 4 X's at the top there, right? Them. Okay. So during the execution of this application, something came in and interfered with our benchmark.
Right.
And it caused these kernel times to actually jump in that area of our bench. And probably, if this is happening on a regular basis, what you'd want to do is look into your environment and see who your neighbors are and see what it is that they're up to help you to understand if you need to move off of that machine or to do something else, right? Some people, when you're looking at virtualization, will look at steal time. In this case, so if you end up getting a lot of steal time, then you know that your CPU frequency is being screwed with by some other application stealing it away from you, right? Well, this is just another indicator. It's sort of a bit of a surprise because you wouldn't actually expect to get this type of information from a garbage collection log, but so be it.
So that's actually taking us back a bit towards the problem that we thought we'd sorted earlier on when we looked at the system environment.
Right, exactly.
And it's an indication that we hadn't sorted that problem out completely.
That's correct.
Okay, shall we go on?
Yep.
All right, okay. So if I go back to the way we're plotting through the different stages you're going to look at with the, when you're doing performance tuning, we've got to the stage where we have, we've figured about the problem in our process, but not in our code. It's likely to be garbage collection. GC is going to be using all the cycles. Or maybe when we've eliminated all those other possibilities, that there's some other process, that there's something else within the VM, or of course that there isn't a problem at all, maybe we've actually discovered there really is a problem after all, and we're going to actually have to roll our sleeves up and profile the code.
Oh, use a real profiler this time?
I'm afraid so, yeah. Okay. Yeah, we really are.
Because I really like the rough and ready one.
Well, we're going to use NetBeans. At least that's freely available and really easy to use. The reason I like using it is because I can understand how to use it, which is not the case with all of them. So let's have a look at let's go over to NetBeans and profile in that. Grep B with collector, IO bound. So, I need NetBeans for that, don't I?
Yeah. We can turn off IntelliJ, right?
We can do that, actually. Yeah, we don't need it any longer. So here comes NetBeans. this is the one I'm interested in. Grep B with collector, because this is the basic code. Let's profile that and see what happens.
Right. Did you edit the filters?
Did I? I didn't edit filters.
Okay, let's stop and just do something.
Right. Okay. So.
Okay.
Right.
So when you go to use a profiler, the first thing you want to understand is, well, get a little idea about how it works, right, and what it's doing. So some profilers will offer you a number of different features. Some of the features include the ability to set points when to start profiling and when to stop profiling. And other ones will offer you these wonderful filters here, which basically says, I'm not interested in these classes, don't include them in the profile. Now, from my opinion...
This is the default, by the way.
The best way to not see your bottleneck in your application is to use these filters, right? If at first run you don't understand where your bottleneck is, really what you want to go in is you want to go into your profiler and you want to tune it back and say, look, stop screwing with the results, filtering it and doing all of these other things. Just give me the raw results so that I can actually really see what is going on. So in this case, the Java core classes here are being filtered out. So you know that read problem that we found in the first when we just used our dumb profile?
Yeah.
NetBeans would have filtered it right out. We would have seen a completely different bottleneck. We wouldn't have seen the read because of this filter. So let's get rid of this filter here.
Get rid of the filter again?
Yeah. Oh, don't think I saw you remove it.
I did remove it. You want to be happy?
Go up to the top.
Well, that's only a defined set.
Yeah, that's fine. Get rid of it. Remove. Done.
There's no arguing with some people. Right. So we're running with. We're really sure we're running without the filter because we haven't even got a definition of the filter set now.
Exactly.
Okay, so it should finish pretty quickly, I hope.
He's really picky about some things. I'm really picky about different things.
Do I want to take a snapshot? I think I'll take a snapshot. Let's have a look at what we learn. Should we look at this?
Yeah.
So it's spending a lot of time in the main method. Obviously, it's spending time in the collector.
Yeah, as I like to say, it's just like follow the big red thing on the right side.
So it's spending all its time in the collector, not because necessarily you can't take it from that the collector is the thing that's actually using all the CPU, because remember that the values don't start passing down the stream until the collector is called, until the terminal operation in general is called. So the terminal operation will always seem to be the consumer of all the CPU. If you look inside it, you will see, eventually we'll see that it's actually calling the intermediate operations. That's what I meant by pulling the values down.
Right. So really what you're saying is that the collector is enclosing everything else.
It's enclosing everything.
Right, and so that's reflected here in the profile too.
Yes, so that's why I'm explaining. Well, the first time I saw one of these, I thought, wait, the collector's using all of my CPU.
Well, actually,
which is actually true, but that's not the point.
Yeah, the code gets so mangled from what you see in the runtime that it's amazing the profilers actually get to properly map back what they see to the actual code that you've written.
We've got one of these again, Kirk. It's all in self-time there. We're not going to learn anything from this. I'll run it again. It's real pain. Sometimes we get results from the profiler that we just really can't make anything of.
Well, that self-time means that it's all spending all the time in collect.
Yeah, but that's not really true. Well, we know it isn't true. Collectors aren't, profilers are just not that reliable, unfortunately.
No, unfortunately not. Sometimes you can get into, like the sampling frequency, I think here is like 10 milliseconds, and you can get into some weird effects because of how the profiler has decided to sample. So what do we got here?
I'm really hoping we won't get the same problem. Oh, we've got the same problem again.
But you have, yeah, exactly.
This is going to be desperately embarrassing if we can't get anything else. It hasn't happened before. Give it another go.
So, like I said before, I think when we ran it before, we didn't actually have Keynote running. Now, the odd thing about this, and this is an actual conversation we've had with Oracle engineers, is that when they run their tests, they actually run them properly on a beautifully set up, laid out machine. And in those environments, the JVM always gets laid out really, really low in memory. And what I've learned over the years is that if you lay the JVMs really down low in memory, then there's things that happen, like the addressing schemes and everything, are completely different. And so what happens is that because the addressing schemes are different and the runtime conditions are different down in low memory, your application runs differently and different optimizations get applied. As soon as you start stacking processes and you start pushing the VM up into higher memory, what actually happens is that the runtime actually starts behaving differently. And we've run into these problems a few times where we're actually trying to do demos and you can't get the effect that you want simply because you've pushed the JVM up in memory and is giving you different optimizations, which means that the whole thing is profiling quite differently than it would. So you got something here, right?
No, I haven't got anything. It's very sad.
Okay, great. We don't have a problem then?
We don't have a problem. Well, you know, we've found a little bit of something, but it's not really. It's not what I expected to see, to be honest.
Yes, exactly. Did you
I'm really on the right one. Pardon? Sorry?
Did you turn Keynote off?
I didn't turn Keynote off.
Okay, let's.
It wasn't Keynote before, but I'm very happy to turn it off.
Yeah. Okay. Just restart
because this result doesn't strike me as very plausible, I'm afraid. Okay.
So obvious demo failure, but as I said before, I mean, there's I think even a lot to be learned about benchmarking
from failures.
From the failures.
It's just as well, really, because we get a few of those.
And from profilers.
Yes.
Yes.
Good point. And from profilers then. Okay.
Is it still running? Yes, it is. Okay, right.
Did you let the profile develop? We just took a snapshot at the end, right?
I just took a snapshot, yeah.
Oh, if you wait to the end, then it accumulates better.
I did wait to the end. I took a snapshot when it offered it at the end. Oh, we're not doing better than this. That's very peculiar.
Could you try instrumentation?
Try instrumentation? Yeah. Okay. Sorry?
There's an option in NetBeans that says profile only project classes.
Yeah, we could do that, but that's sort of cheating. Actually, that's completely cheating. Yeah.
Okay, try this.
Maybe the version is the fixed one.
We had the filter turned off too when we profiled before.
Is it the fixed one?
Okay, so just let it run to the end then. Okay.
I have been letting it run to the end.
Yeah.
Well, maybe I'd like to actually check whether this is the right code. Okay.
I was thinking that in the back of my mind.
Yeah, I'm wondering if have I got the right code? It's okay. Looks like the right.
Okay. Yes.
Right. Okay, so certainly looks like the right code. I'm going to have to give in and say what we expected to see.
Yeah, the last profiler.
This should be reading. Let me just check. It really is reading from the buffered reader. It's actually quite a puzzle. I don't understand why it wouldn't be. I'll tell them what I expect.
Yeah, we'll hand wave through this problem right now.
I'll hand wave through the problem. I don't understand why the profiler isn't showing. I mean, the profiler results aren't actually inconsistent with what I expected to see. They're just not showing what I expected to see. Yeah. What I expected to see was that it was going to be spending most of its time in I/O. Right? Because what I'm doing is I'm reading a huge number of lines from streaming I/O file. This big file's got I don't know how many millions of lines, it's megabytes, and that should and almost certainly is actually dominating the performance of the whole application. Now, the problem isn't that the profile is showing something different. The problem is that it's just not showing anything. It's just saying it's all in self-time. That isn't really very plausible that would be the case. And we're disappointed because we weren't seeing this before.
We ran on a small file before, right?
Not this one.
Not this one.
Not
okay.
this one, no.
Sure. Okay.
So I think we're just going to have to hand wave over this one.
I think so. There is some really interesting things that optimizations that have occurred that help solve the issue. Is that disks are just well optimized to read from left to right. Right? They'll just buffer that up like really, really quickly. And so if all of this stuff is still up in your buffers, like in your kernel buffers, then like the IO buffers, then it could basically wipe that bottleneck out of the picture here. And generally, which is a consideration. So when for the benchmarks that I was running, basically I went and found the code, then I put it into the benchmark that basically said, wipe out the caches clean, right? So that we're always starting with a fresh, non-initialized cache, so that you could see the effect as if you're reading an unknown file in your application.
Yeah, I mean, it's a good story. Kirk did tell me to restart my machine. But then he said I didn't need to, so whose fault is it really?
Mine.
Oh. Well, hey, we've got an audience.
Okay.
that never happens usually. So the idea was that the profiler has not shown us what we'd have liked to have seen, but we expected that it would say that it was that we were I/O bound, and what we would really like to figure out is how could we get around?
Oops. Backwards.
I've gone backwards. Okay. How can we get around this problem?
No, I mean you're backwards here.
I'm backwards.
Oh no, you're up there.
Oh, so I am. Oh,
okay.
I'm still mirroring.
Yeah, exactly.
Oh yeah. Well, once things go wrong, they go wrong.
No, it's fine.
Let's see if that will work. Does that work? Oh yeah. Right. So streaming I/O is slow. Actually, believe it or not, streaming I/O really is slow. And when I was thinking about this problem for the book, I was just thinking like, if only there was a way of getting all that data into memory. But I just couldn't figure one. What do you think, Kirk?
Well, I think
it's out there on the disk. Well, or on the
Well, I mean,
drive.
the first problems that you sent me were kind of interesting, and we did a lot of profiling on them, and we came up with some interesting results. But I think the I/O problem, I mean, the theory is that if you could mmap the data into the process, then
that would be a good idea.
That might be a way of alleviating the I/O boundedness of this particular problem.
Okay, so that sounds like a pretty good idea. And, I mean, fortunately, Java NIO provides you with a very direct access to operating system's ability to map files into memory. So that, but essentially, you can treat them as though they were in memory, and that should speed up this streaming I/O problem quite a lot. Now, the problem with the next demo, where I've converted the previous one to using a mapped byte buffer, is that it should show that things are better, but since we didn't really see how bad they were with the last one, that's kind of frustrating. Let's give it a go anyway. This is grep-B with collector and mapped byte buffer, but we're still sequential. And let's hope that maybe we'll get some more information here about it, about what's going on.
Do you want to mirror?
Pardon?
Do you want to turn the mirroring back?
Oh, turn the mirroring back on, yes.
Yeah, okay.
Thank you.
No problem.
I always need to be reminded of this.
It's fine.
Okay, so that's now running, and in a moment it'll offer me a snapshot, and perhaps, who knows, this will actually show something. Okay, so so we're in the collector. Have a bit of a prayer. It's just one of those days. It's just not going to tell us anything now. That's absolutely bizarre.
Yeah, well, it did run faster.
It did run faster. Yeah, well, there's more hand waving, and we don't understand this. I think, we'll have a break in a little while, and we'll put our heads together over this because it's kind of irritating. The idea of getting it into map byte buffer definitely improves matters. It actually brings us to pretty much the end of what's possible for us with this line of attack. So.
Yeah, really. I mean, if we go back to the CPU chart, what we could see is that when we're running these benchmarks, we're basically saturating one core. And as I said, there's a lot of black left over, and I'd really like to fill that black in with green.
Yeah,
Okay.
that would be better than footling around at the bottom as we are doing.
Right. So how are we going to do that?
Well, the does this work? Cool.
Yeah.
Okay, right.
Excellent.
So we've kind of gone through a number of iterations where either in practice we found the bottleneck, or we found it in theory and waved our arms about that, and we've kind of reached the end of the line really of what we can do with just stepwise improvement. There is another possibility that instead of just we've found the bottleneck again. Well, the bottleneck now is that the bottleneck that we were seeing until we tried to run this in real life was that we were still. Even though we were reading from memory, the IO was still dominating. We were starting to see the intermediate operations coming up as problems, but still IO, which was happening through a single thread because we're on sequential streams, was still dominating. So that's still the big bottleneck. So there's not much more that we can do than getting our data out of memory. We can't go much faster than that, unless we maybe have a bright idea. So a possible bright idea would be to actually release the constraint where only a single thread is reading the data and only a single thread processing it, and think, well, maybe we could use more than one thread. And why would that help? Well, the reason that would help is because the chip that Kirk showed you at the start of this talk is now looking more like this. So this is an Intel Xeon E5 2600 10-core chip. Everyone will be familiar with what's going on here. This one's already 2 years old. The base clock rate is quite high. It's higher than the clock rate was on that Varian 620i that I showed you at the beginning. It's about upwards of 3 gigahertz. So that's not too bad, but there's 10 cores there. Why is there 10 cores? Well, there's 10 cores that basically, I'll tell you first of all what the problem is with the chip, and then I'll tell you why we've got to this. All that stuff in the cores are the stuff that are along the top and the bottom. And all that stuff in the middle is cache. And the reason it's there is because the memory bus is much slower than the processor speed. So getting data from main memory into those cores is the big problem. And increasingly, on modern chips, huge amount of the real estate is given over to cache, because the big problem is to keep them fed and to get that thing that Kirk wants, the big green area onto the processor graph. So this is actually this multi-core has created this huge problem for us. And actually our central problem in Java, or a central problem of the Java architects, is how can we use it? How did we get into this situation? Well, I first found out about this a while back, but the situation has been obvious to some people for a long time. In 2005, Herb Sutter wrote a very famous article called "The Free Lunch is Over," which the URL is there because I think everyone should see it. And the key point about that was the graph that you see on the right-hand side there. So the green line is the number of transistors in chips, and it just goes up exponentially, exactly as predicted by Gordon Moore all those years ago. 50 years of continuous progress in the technology in exactly the way that he described, pretty much doubling of the number of the density of the transistors every 18 months. It's just an amazing piece of progress. There's never been a technology like it. And for a very long time, we used to think that the processor speed would follow it. That's the blue line below the green one. And you can see that in the early 2000s, it leveled off, and it's going to stay leveled off.
Can I add something? Add something bits here, right? So it's interesting that if you look at the green line, it's still traveling up like that, and the processors have leveled off like this, right? But the real key metric to consider is not really the clock rate; it's actually the instruction retirement rate. And Martin Thompson did a brilliant study where he actually...
What's the instruction retirement rate, Kirk?
Well, that's the rate at which the CPU can retire each of the individual machine code instructions that it's functioning through, right? And then generally when you're looking at these types of systems or transactions and things like that, then you're focusing on what the retirement rate is. What's the ability to just continually keep finishing bits of work. And as I've just mentioned, Martin Thompson did a really nice study where he took a text processing application and he ran it on a whole bunch of different processors. And what he found was that although the clock speeds had dipped and had fallen, the instruction retirement rates had actually still increased close to what the green line was doing. Okay? Which means that the CPU manufacturers themselves have compensated for the fact that clocks have gotten faster by putting more intelligence into the chip in order to maintain high instruction retirement rates. So that means you still can get faster and faster processing for free. But that when we start relying on that, I mean, that's really, really hard. There's a lot of really, really hard work that has to go into the chip design in order to keep that curve going. So eventually, that free lunch is going to run out also
as well.
Yeah.
I like to say that when the transistor was born, it had like in the old fairy stories, it had at its christening, it had a good witch, and a good fairy and a wicked fairy at its shoulder. Here's the good fairy. The good fairy says. Actually, I thought of God's blessing to Abraham. He said, "Your descendants shall be as numerous as the stars of the heaven." That was Gordon Moore's blessing on the transistor. You're going to have double the numbers every 18 months. That's even faster than Abraham was able to reproduce. How did it? Why has this happened that they can't go faster? I know they actually are going faster, but clock speed's not going to go up. Well, what's the reason for this? Well, the reason is physical limitations that are just not going to be released at all. The narrower the channels become, then at high frequencies, the more signals leak from them on the chips. The problem of heat dissipation is enormous. For a while, we thought we were actually going to get water-cooled chips because the amount of heat that they're generating is so great. And again, that has to do with clock frequency. And the real killer, bizarrely enough, is the speed of light. There's really not a lot you can do about that. Light can only travel in in a vacuum. Light travels 30 centimeters in a nanosecond. So on the chip, it's going to travel a lot less than that. So actually getting information to a single core at higher and higher clock speeds isn't really going to work.
Yeah, but they could still keep increasing the clock speeds. They just can't deal with the heat. So, so we worked with a number of clients that will actually overclock their CPUs, and then they will fix the clock frequency, right? And that works really nicely because that means that your CPU is always hot, always ready to run, and that means you can get really, really fast responses, like in the microsecond range. The only problem is that they have to keep replacing the hardware at a very high frequency because they just burn the chips out really, really fast. So these things might run for a month or two, and then it's basically burnt out, throw it out, put a new one in.
Right. Okay. That may not be much of a strategy for the ordinary user. We're not going to get faster cores. We're going to get more cores. They may be a bit faster, but the key thing is Moore's law is going to carry on, and we're going to get more cores.
More cores, more cache.
Yeah. So what we would like to see, I mean, ideally, the way we'd like to take advantage of that if we could, and the way that C programmers can take advantage of it maybe, but that it's much harder for us as Java programmers, is to attach a thread to each one of those cores and have them working independently. And then, obviously, that if you could manage that, in the ideal case, that 10-core chip that you saw there is going to get through 10 times as much work as if only one thread was working. Here's my visualization of parallel streams. And parallel streams, by the way, is the mechanism through which one mechanism, at the moment the main mechanism through which this is going to be accomplished. So now we've got two values coming up. You want to think that these really, I've shown them as single values here, but obviously it's not really worthwhile breaking down an array with 4 values in it. You would need more than that. So each one of these now represents really a segment of values. And so so they're getting transformed independently and getting filtered independently, and then eventually they're getting collected. And obviously the collector has to do some clever work to make sure that even though they come in random order, as it were, that the order of what we call the encounter order of the data is preserved. So that's the basic picture of parallel streams. how they work. And now we're looking for a parallel solution for grep minus b. As soon as I say dot parallel stream, a number of things happen. I'm released from the constraint of streaming I/O, and streaming I/O coming from memory suffers from this. If it's a single being executed by a single thread, streaming I/O, then it suffers from the same constraint as so the same problem as streaming I/O from disk. It's just faster, but it kills parallelism in the same kind of way. This lets me put up my favorite or least favorite graph, which is a graph about Amdahl's law. I find this incredibly depressing. For once, it's projected big enough for you to make out what it's saying. The idea is that if you increase the number of processors along the bottom, you would expect the speed up, or you'd hope that speed up would increase linearly with the increase in the number of processors. And that's the blue line. That's if all your code is completely parallelizable. Let's say it's all independent. It can all be executed independently of everything else. But if there's 1% of it, even 1% that has to be executed in serial, then the red line below is the one that is going to be.
So, yeah, I can make that red line even more real than it actually is in this particular chart. So assume you have a 24-core machine, right? And you have 1%. So that's basically 10 milliseconds, 1 second of contention in your algorithm, right? That means that of those 24 cores, you're only going to be able to reach 19 and a half of them. So 4.5 cores are just going to be sitting there idle, and there's nothing you can do to get to them. It's just practically, they're practically, for all practical purposes, they're just sitting idle, doing nothing, and you won't be able to reach them.
Yeah, and in fact, you know, like 1% serial is incredibly ambitious. I mean, even 90% parallel to only 10% serial, which would be, by most people's standards, a pretty well parallelizable algorithm, is only going to use at most. You're only ever going to get a speed up of 5 times, no matter how many cores you throw at the problem. So I think of Amdahl. If Gordon Moore was the good fairy at the birth of the transistor, then I think of Gene Amdahl as being the wicked fairy. So Gordon Moore was saying your descendants shall be as numerous as the stars of the heaven, and Gene Amdahl saying, but it won't do you any good. So here's my solution now. Here's my second solution, or I suppose my 20-second solution for grep minus b. We're going to implement a splitterator. This is how all streams are sourced. They're all sourced by splitterators, except the fact a splitterator is made. It has 2 functions. It can split and it can iterate, kind of obviously. But for sequential streams, the iterative part is the only part that's used. But if you want to go parallel, then the split part of the splitterator comes into effect. So here's a splitterator, and the brackets on the underneath show the range of data that it's covering. The data's along the top, and we have 2 splitterators there that cover this range, and then each splitterator is capable of splitting itself, and it creates a new splitterator, like an amoeba splitting off, and that new one gets given half of the range that the old one had, and so on. So eventually you get broken down to separate sets of data. If they can be processed independently, each one of them be given to a different thread, and then each thread will process these segments individually, iteratively. Right? So the idea is that each one of these different colors will be assigned to a different core, and in the ideal case, you'll get perfect parallelization. So I had to think about how I could have a splitterator over this map byte buffer. There wasn't one in the JDK when I was writing the book, which was after JDK 8. But before JDK 9. So I invented this thing which I called a line splitterator, and it was a bright enough idea. I'm quite proud to say that rewritten and considerably improved by Paul Sandoz. It's actually in JDK 9. So I was really looking for an example of something that I needed to do. So they kind of took it away from me. So now I don't have a plausible example any longer. So the idea of a line splitterator is kind of obvious. You start off with the splitterator coverage extending across the whole mapped byte buffer, and then you take some random point in the middle, some midpoint, and then you just go and search for a line terminator, and that's a suitable place to split. So now the splitter splits itself into two, like an amoeba, and the new splitter gets coverage of the bottom half, and the old one just takes coverage of the top half. And this actually gets significantly better performance, because now with this line splitterator we've got two big advantages. First of all, we're not constrained to only a single thread reading from the data in, but also, as it happens, it really helps my algorithm, because the collector becomes a lot more simple. Because the splitterator already knows the displacement of its coverage, and therefore of each individual line. And so we don't have to do that calculation that the collector did. The collector becomes a lot more simple. Oh, didn't mean to do that. But as you can see, the next thing that's going to happen is a demo. So let's see whether I can finally get a demo that will actually work. Demos don't usually work for me, so I'm not actually very surprised about what's happened, but it's a bit sad.
Yeah, actually, we ran this.
Okay, so I'm looking for grep-b with splitterator.
Are we going to show the CPU?
Are we going to show the CPU? We can show the CPU if you like.
Yeah, let's show the CPU.
Let's show the
I always
CPU.
like to see the CPU.
Okay, right, so there it is.
Awesome.
Okay, and let's run this, and please show us something this time.
Actually, are you...
What have I done wrong?
Nothing. You're profiling.
I'm profiling.
You just ran the profiling.
I did just run the profiler. Don't I want to run the profiler for this?
No, just run it.
That's okay. I mean,
It's okay. That's good.
at least we're seeing something good here, aren't we?
Yeah.
We're actually seeing that the time's been divided between the different threads in the fork join pool.
And it ran a lot faster.
And it ran a lot faster.
Yeah.
This is actually that was running on the same size file as the last example, which didn't work. So we've achieved something here. I mean, actually, we've achieved quite a lot. It really does run a lot faster, and we are actually dividing up the work in the way that we want.
Do you want to go off script a bit? Since we have a profile here, let's see if it works. Let's just tunnel down and see what it actually looks like.
I didn't dare. I don't want to. We had such bad news out of it. Part of the problem is that the stream code isn't easy to understand. I mean, you really need to sit and look at it for a very long time to be confident that you know what's going on. What would you like to look at?
Well, there you are. Let's just see where it takes us. That's all.
Okay, that didn't take us very far. I'd love to see the regular expression pattern matching coming in, but I'm not going to.
No, we're at the line splitter, and we're at the reference pipelining section. There it is, right there. You got your wish.
Found it in
you
the
got
end,
your wish.
yeah, that's right.
You finally got the matching.
It's not actually very much. So one of the things I'm unhappy about when I see that is that this still isn't a very great example, and the reason is because the reason it's not a great example isn't because it didn't work, because actually it sort of did work this time, but because there's only any point to doing this splitting. There's quite a significant overhead. Kirk's going to talk about this a lot more. There's a significant overhead to going parallel, because you've got to set up the fork join framework, and then you've got to get the splitterator to do all this stuff. And the payoff comes basically when you've got expensive intermediate operations and you're executing those in parallel.
Yeah, and I think this is a really good example.
So my irritation about this is that the regular expression matching, which is meant to be like a heavy payload for an intermediate operation, isn't heavy enough. So Kirk's going to talk a lot more about when it's worthwhile to go parallel.
But it's interesting to see that that this profile has actually changed. Where before we just pretty much went into the collector code.
Yeah.
We have all of this extra stuff here that makes the stack trace a lot deeper, and that's really just overhead framework code.
Yeah, that's true. A lot of framework code there.
Right.
So we get some things out of it because we see the different threads working.
Yeah.
We see the overhead of the framework code, and we do see the regular expression pattern matching. Oh,
excellent.
Okay, cool. Something's worked a bit. Right, so I'm just about done with this, and I think you're probably ready for a break, is my guess. Let me just see whether...
I know I am.
You're not supposed to say that.
And I haven't been doing anything yet.
That's right. So I'm about done with this development. The next part is going to be Kirk talking about doing this stuff in the real world, because I've been looking at it in isolation. As you can see, we've been in the micro benchmarking environment. I've been trying to get the machine quiet, and that may well not be the real life situation. But just to round up, then, the line splitterator is the splitting action is log n, which is a big contribution, let's say, because prior to this, reading the data was all of it order n, and the improvement in the collector is considerable, which just helps my particular job. And the result overall wasn't too bad. I mean, I found that the sequential stream was faster already than the iterative solution, which is a considerable tribute, I think, to the guys that implemented streams. But the parallel stream actually was 2.5 times faster, which is not bad, I think, for 4 hardware threads. And that was a pretty robust result, not done under these kinds of conditions. So I've just got a couple of more words to say about what it's like parallelizing streams before I hand over to Kirk to talk about the real world. When you're thinking about whether it's worthwhile parallelizing streams, you have to also think about the kinds of intermediate operations you've got. If they're all map and filter, you're really in business, especially if they're kind of expensive map and filter. That's really important. Some of the operations are parallel unfriendly. I mean, the worst example of this is sorted, which is a complete barrier to parallelism. So in order to sort the elements of a parallel stream, they've got to be accumulated in an intermediate data structure. So that's not great, and that's kind of a killer. There's some others that actually are worse than you would expect. They're typically the ones that require some kind of ordering. You don't necessarily think of these things as being parallel unfriendly, but something like limit, for example, which seems like such a straightforward operation, actually turns out to be really difficult to do if you're going to make it equally doable in parallel, because limit takes the first n values from a stream, and that's perfectly straightforward if it's sequential. But if it's parallel, you've got to think, well, remember that the uneven progress of the elements across the diagram there in the animation. How do you choose which are the first 10 or 50 elements? That's really pretty tough, and it really doesn't work very well. I mean, it really hurts the performance of parallelization. And the last point is a kind of general piece of advice I give is that collectors are actually can be quite expensive. They can be a big expense. So with things that aren't maps, the to list and to set, the performance is going to be dominated normally by the accumulator. The accumulator is typically going to be called many more times than the combiner. So if you've got like 10,000 element array, then the combiner is going to be called for your if you've got 4 cores, it's going to be called like half a dozen or maybe 10 times, something like that. Whereas the accumulator will be called 10,000 times, or of that order. So it's probably you probably need to worry most about the performance of the accumulator. But there are 2 provisos to this. One of them is if you are doing parallel streaming into a non-thread safe container, then like array list or hash set, then the framework has to manage thread-safe accumulation into that container, and there'll be an overhead to that. You may think that a good alternative then would be to supply your own thread-safe container, like a concurrent map, or typically it will be an implementation of a concurrent map. And you can do that, and then you hit a different problem in that case, because map merging turns out to be fiercely expensive. So, in general, I mean, actually, map merging is fiercely expensive for any map at all. So, pre-sizing data structures that streams are going to dump into, I found that was really important, and you could get very much better results. Of course, pre-sizing means you're pre-sizing all the intermediate ones as well. So that's not going to work if you have a very large number of cores. But typically on 2 and 4 core, 8 core machines, that pre-sizing is probably going to be a really good bet. It'll reduce the number of resizes of the map that you have to of the map that you're dumping into that you have to do. So those are my kind of preliminary and kind of pretty sketchy conclusions. I've got some more at the end. On the agenda, we've reached the point where Kirk is going to talk about fork-join parallelism in the real world. I think you guys need a break. Am I right?
Absolutely. So I think what was the standard break time?
It's up to you.
Was it 15 minutes or so? Yeah.
50.
15?
Okay.
50?
No.
What are you trying to do to me? Okay. 15 minutes then, and we'll start up again. So that's 70 on the counter here.
Okay,
71.
15 minutes.
Okay. There you are. We're back. And surprisingly, you're back too. So that wasn't I guess you didn't have enough punishment for the first one. Okay. So where are we on our agenda? So, okay, I was supposed to talk about fork-join parallelism in the real world. One of the things that motivated me about this topic was I was watching all of the wonderful speakers talk about lambdas and serial and parallel and all of this great stuff, and they just take all of this code and they basically say, and now we can go parallel, and life will be good. And I just looked at it and I said, oh my God, he just didn't say that, did he? Okay. And really true to form, I guess I was in Chicago in January. I was talking to some people out there, and they were using Java 8, like really early adopters of this. I should say adopters, and they were using Java 8 really early on, and they took all of their code and they lambdized it, and guess what they did? They said, fantastic, we can make it parallel, and they deployed it. Yes. And then they quickly wrote a sed script to go through all of their code and turn the word parallel, or basically, grep it out of the code. Really, what were they doing in this case? Well, they were doing something like this thing here. So what I call it something like a simulated server environment. So in this case here, we're not going to be parsing text, doing all of these like complex manipulations that apparently are fairly trivial to understand. I have to say that I have a hard time understanding them myself there. But so if you did,
it's just your problem, Kirk.
Yeah, I know it could be just my problem. Absolutely. So I like to do simple things. In this case, even there are what I consider to be fairly heavy instructions in here, in the sense that I'm doing pattern matching and searching, filtering, and parsing and all of this other wonderful stuff in here. But what happens in an isolated environment when I run this piece of code? Well, in an isolated environment, I can run through a 2 gig file using Maurice's wonderful line splitter, at least the Java 9 version of it, in about, I guess about 2 seconds, right? So the question is, when I start loading this up, how does this perform? Well, there you go, right? We have a max time for an individual job to clear through this simulated environment of 39 seconds. I certainly had one that was running down like about 9.2 seconds. The median seemed to be around 22 seconds. I didn't actually do a calculation. I just looked at the numbers and said, okay, I see 22 more often than anything else, so that's the median. Right? What's that?
That's not a median.
That's a median. It's the thing you see most often, right? Sort of.
No, Kirk, it's not.
In my books it is. Okay. Anyways, it's not a real median, but it works well. Okay. And notice the CPUs here, right? I mean, you remember I said I don't really like to see a lot of black in this course? Well, this is sort of an indicator of another problem, right? When I don't see any black at all. So I was able to like completely saturate the cores, and there's not a lot of system time in there. So really reading the file in this case, because of the wonderful line splitterator, works really well. So what is the problem that we're really facing? Well, I sort of tried to generally categorize this thing as to something which I call the tragedy of the commons. And I guess the initial wonderful cow photo that Maurice used was sort of motivated by the fact that he wasn't too keen on this particular one. But I like it, you know, there's one flower, two cows.
That picture actually was the original, on the cover of the original book by Garrett Hardin.
Yes.
So it's the original.
Yes.
I think it's fine.
Yeah.
It's lovely. The idea of the tragedy of the commons, not everybody's heard of it, and Kirk always assumes that everybody has. The idea of the tragedy of the commons is that if you've got lots of people all pursuing their own interest on a common resource, then actually everybody will may well suffer in the end. So like everybody puts extra cattle onto the common grazing ground, and it gets exhausted because it's never in any individual's interest to hold back. They think, oh, if I just add one more cow, if I just take one more aeroplane flight, if I just, you know, then what difference is that going to make? But if everybody makes the same decision, then you end up with the common resource depleted.
Right, and you know, and there's been a lot of discussion about this particular phenomena since then, but generally it's recognized that, you know, just as he said, like if everyone is making the same decisions, then you can probably run into problems very quickly. So the tragedy of the commons in our case is really the fact that we don't live in an infinite compute environment. We have a finite amount of hardware, and the amount of hardware we have is going to, you know, it's going to bound us to certain constraints. So it might be in your best interest to grab it all, but if everyone behaves the same way, I mean, this goes back, the funny story I have, well, at least it's funny to me, that I have is that when I was working on Cray supercomputers, it's a computing environment that had no swap. And so, so it was very expensive to context switch between processes. So the operating system was just tuned not to do it. And as it turns out, if you were a small process, then it would look at it and say, okay, well, we probably can't swap you out. But if you're a big process, then it's definitely not going to swap you out because that's a very, very expensive thing to do. And you know, we were paying incredible amounts of money for these pieces of hardware, so you didn't really want to waste any cycles on it at all. And so what I quickly learned was like, fantastic, if I want my applications to run fast, I don't really care about the other guys, right? I'm just going to allocate like this huge array thing, use a lot of memory, and then all of a sudden, you know, the machine is actually mine. So I wasn't really what I would call being a very good neighbor in this particular case, right? So really what we want to do is when we start looking at, you know, do we parallelize or do we not parallelize, you know, we want to have this notion as like, you know, what is the environment that I'm in? Am I actually being a good neighbor? Okay. So as we saw from the previous profile that I randomly had Maurice open up, that a lot of the code on the you know, a lot of the stack trace was just dedicated to framework code, and in this case the framework code is fork join. So really what we have here is an exceptionally complex piece of code like fork join. It's fairly complicated to use. Being made really accessible to everyone, because basically if you want to use a fork join or set up a fork join, no problem. You have a data source, you have the parallel keyword, right? So you can stream it parallel, and then under the hood, as you can see, what was happening is that all of a sudden all of our work is being magically parallelized by all of this framework code that we're just taking advantage of. You know, basically, how does all of that work? How does that all fit into this particular picture? Well, the way the fork join framework works is that I'm going to have this common pool. And in JDK 7, what we ended up with is this common fork join pool. And if you look at how it's configured, you know, that's the default configuration there. Is that the right font for 1?
No, not really, but
okay.
Tell them it's 1. And
it's 1. That's a 1, not an L or an I or whatever else you might think it might be, right? So that means on this particular machine, I'm actually going to have 3 threads in the common thread pool. And so here's some properties that you can use in order to change that if you like. Now, generally we don't really recommend that people change this to make it bigger because it, well, one of the comments I had during the break was saying like, okay, so your application was I/O bound, yet having more threads made it run faster. Now there's a whole bunch of conditions under which that can happen, but there's many more conditions where that's not going to happen. So if you're already I/O bound, generally adding more threads to that problem is actually going to make the problem worse because you're putting more pressure on the I/O channels. In this case, I think the operating system and the caches and things like that saved us. And the expense of the intermediate operations provided enough of a gap that it made sense, and we were able to take advantage of many threads. But that was this particular case. In most cases, what we find is that that if you have a bottleneck and you just add more threads to the situation, it's just going to put more pressure on that bottleneck, and that's going to make the performance worse. Which comes to another point, right? If going this way didn't work, let's try going that way. Which means if adding more threads is going to make the problem worse, we might want to actually tune this down so that we're actually using fewer threads. Now, there's another way you could do that, but it's generally not a recommended way, and that is instead of using the common fork join pool, you can set up your own fork join pool, and then you could submit the job to that particular thing. The reason why that's not recommended is now that, again, we run back into this particular situation where if we have everybody doing this with their own fork join pool, then you have absolutely no control over what's going on. Right. So how fork join works and how it performs is now going to be really, really important to the latency picture of our applications, right? Because it's going to be intimately involved with how our application is functioning, right? There's a couple of differences here, I think, in the fork join API that we can talk about. First is this fork join invoke. So when we invoke a fork join task, right, essentially what's going to happen is that we're going to submit this task into this pool, and if 100 threads are all going to call invoke, then essentially we're going to have 100 plus all of the fork join threads basically working. So in other words, the invoke is going to capture the submitting thread and say, let's use it as a worker thread. If we just use sorry, that was the invoke, yeah. So if we just use a submit, then essentially what it's going to do is it's going to say the submitting thread is going to be released, which means that somehow we have to figure out how to get the results. So sometime in the future, we actually have to go and do a get call in order to get the results out. Again, if we have a lot of people actually using this fork join pool in this way, then they're going to be spending probably a lot more time waiting for threads than actually processing. And again, that's going to add a lot of dead time to your latency picture. Another issue is that the fork join comes with a significant overhead. So the profiler should have shown you that, okay, there's a lot going on in here. And really what that means is that each chunk of work, we're going to take our overall data source, and we're going to chunk it into different segments, right? Until we get down to some atomic size where we say, okay, that's small enough now, let's go and do the work. But so whatever the chunk size is, it needs to be large enough to sort of cover the costs of all of the overhead. Otherwise, it's not setting up for parallelism. So one of the examples that Maurice sent me was some text processing. It was quite some time ago, so I can't remember all of the details of it.
Was this the example from Guy Steele?
Yeah, I think so.
That's right. So it's a word splitter. That was it. That was the idea of it. It's a very famous example from a talk that he gave, which was actually an inspiration to the Oracle team that implemented implemented streams, because in this talk he explains that that removing the ability to handle hardware constraints from the programmer actually gives the programmer gives the compiler more wiggle room to generate really good code. And the examples are, if you don't know anything about, say, absolute data addresses, then you can use symbolic addresses. Assembler represents the removal of your knowledge about exact instruction addresses. And he goes down this list of various improvements that have been, and he comes eventually to the one that is preventing us from preventing automatic parallelization. And this was a big inspiration to them. So the big thing that is preventing automatic parallelization is the use of iteration and accumulators. And that was a big motivation for why accumulator variables aren't allowed. So he has this brilliant example which he builds up in Fortress of how to of a word splitter. It's very elegant. It's really beautiful. And I thought, well, I'm going to do that as a centerpiece of the demonstration of the Stream API for the book. And I was very excited about it. And I made the mistake in writing the book, and definitely don't ever do this, of leaving all the performance measurements to the end. That's a really bad idea, because then you got to the end, I discovered the performance of my implementation of this was so awful. Absolutely, it's like fit for a blog post about how exactly not to do that. So that was the example that I sent to you.
So
I was in despair, and I had to rip out half of the central chapter of the book.
It was quite funny, because he was like really all depressed, because the first thing he said is, "What's the problem here?" And I said, "Okay, well, you haven't amortized the overhead costs of the fork join in the workload and everything like that." And he was like really depressed, and I'm going like, "No, this is exciting. This is fantastic. It's a great result that basically shows." Cases that you shouldn't use for, this is actually a poster child for, when not to use fork join, which I think is also as exciting as coming up with good examples as to where fork join actually works. So, so what is the rule that we use for deciding if we are actually going to parallelize it? Well, one of the rules, I should say. And that's the CPNQ performance model that I think was published by Doug Lee. We have a reference for it in the back, right. So basically what we're saying is that we need to consider the number of submitters, the number of CPUs, the number of requests, and I think probably the most important factor here is, well, besides the number of CPUs, is the cost of the operation. So the workload of the intermediate operations has to be about, was it 100 microseconds?
That's what the Oracle team thought. I measured it as a bit less than that. But
yeah, well, it's something. As soon as your operations start, your intermediate operations start taking less than that amount of time, then the costs of going parallel might outweigh the benefits that you're going to see. So generally, it's a work unit size of about 10,000 items. Yeah. I think that's very much a rule of thumb. Exactly.
It's really not going to work. So, for example, if you've got some chess program, or I don't know, something that's calculating large primes, you don't actually really need very many of them to make it worthwhile doing it in parallel. So, the 10,000 number is I put that in to please you, but that seems to me to be pretty much of
it's really a rule of thumb.
Pretty much of a rule of thumb.
Which is why I insisted that you put the 100 microseconds back in there, because I think that's probably a much better measure. You can look at your intermediate operations and then do some sort of estimate to say, okay, are they going to take about that amount of time to complete? If they are, then probably, this is a task that we can consider putting into a parallel environment. But that's only going to be one of the aspects of the decision making. There's many other things that you have to consider. First, again, you have to consider, okay, what is everybody else doing on this machine? Because if I consume all of the resources, am I leaving resources for for other people to get their work done also? I guess in today's Amazon world, you'd probably just spin up another virtual machine and do it over there. But then, of course, I always like to say you really don't virtualize yourself into more hardware. Right, okay. As we saw earlier in the presentation, quite often the CPU is not the limiting factor. There's something else going on. So what we're looking at with fork join is we're looking for tasks that are CPU bound. That's where it's going to work best. If you're not in that condition, then your throughput of your application is going to be constrained by some other resource. That's some other resource is going to come along in and cap the throughput of your application. And one of the other resources that can really put a serious cap on your throughput is how much pressure you're putting on the kernel. A lot of the activity in the kernel is actually single-threaded, and the kernel actually will have to do a lot of maintenance on its own. The JVM does maintenance, the kernels actually do maintenance. And when they do maintenance, they shut everything down and they just do their maintenance. Fortunately, these things are very quick, but they do add a lot of jitter in your environment. So if you're an environment that's jitter sensitive, then this might be, you basically want to look and say, okay, like how much pressure am I putting down there? How much work am I getting the kernel to do? A lot of source of serialization will actually come in the kernel code. In this case, more threads are probably going to decrease performance because we're going to put more pressure on the problem, right? And this is predicted by Little's law. So we talk about Amdahl's law, Moore's law, and I think the third law that's really important in this, that describes things that happen in this particular topic, parallelism, is Little's law. Right. So with the common thread pool, essentially what we're going to say, what we're saying is that if we are going to submit a job to the fork join pool, we're going to consume all of the threads in the fork join pool. So most of the algorithms are designed to actually just consume everything that is there. So the performance is going to be tied to whichever resource we run out of first. If we run out of worker threads, then we're just going to have to wait for more threads to service our task, right? Or if we've run out of I/O bandwidth or network bandwidth or whatever it is, the resources that we're constrained to, then that's constraining us, then that's going to really that's going to be the thing that limits the performance of our application. So as I said, when you submit your task, it's going to consume all the threads. So this is what I call like the all hands on deck implementation, right? Everybody's now working towards the common cause of getting your job done, right? So that means we have a queue, and when we have a queue, we generally talk about a whole bunch of different laws like Little's law, Markov, all these guys, right? And so what I did with my particular task is I said, okay, well, let's submit a task every 500 milliseconds, right? Or, well, it's 2 per second. So I can now use Little's law here to basically say how many tasks that I have in the system. So this, on average, I have like 5.6 tasks, right? So if it takes like 2 seconds for a task to clear, right? What you can do is you can start using this value here to say, okay, how much processing time am I actually getting, and how much dead time am I accumulating because of just the dynamics of the system here.
So the usefulness of this is primarily to calculate latency?
Yes, exactly. So if you want to actually reduce the latency, then what you need to do is you need to figure out either, well, these are the parameters, right? We either need to reduce the service time, right? Reduce the arrival rate somehow. Or so the reducing the arrival rate is when we might bulk up, because some operations, like if you look at round tripping on a network or whatever, for like I don't know, like recent problem we had was just result set processing, right? So we could actually make the result set bigger, which meant we did less round tripping.
So the arrival rate was less? So
the arrival rate was less, and the actual processing time of processing the larger result set wasn't significant, so we actually ended up with an overall reduced service time, which meant that we could lower the number of tasks that were actually active in the system over time, right? I mean, the only other way you can actually do this is to add resources to the system so that you can actually have more of these tasks in, basically in flight, right? So these are the tasks in the system. You're going to look at it. One is going to be active because it's going to be consuming all the threads. The other 4.6 are going to be sitting there basically twiddling their thumbs, waiting for the resources to free up so that they can continue forward. So this is a way of describing the system. Now, and this gets into something that we talk, that I have slides on later, but I'll probably just bring it up now. Anyways, is that unfortunately, if we look at all of the framework code we have in Java util, well, concurrent and well, all the other things that support fork join, is that we have no instrumentation there. We have absolutely no clue as to what's going down inside the fork join unless we actually use a profiler. And we generally can't use profilers in production environments for obvious reasons. But without this type of information, then it gets really, really difficult to understand what your latency picture looks like. So if I'm building a time budget to say, okay, where am I spending my time, and what is it that I'm doing? I have this black hole. As soon as I submit into here, unless I do some sort of external timing as to what's going on, I don't really know what's going on. And even then, I don't really understand, right? Am I actively processing, so it's just taking a long time processing, or am I sitting in a queue just accumulating dead time? You know, what does the latency picture look like? Generally, when I'm performance tuning, what I find is that the biggest gains that I'm getting in a system are reducing dead time, right? Finding places where the application isn't doing something when it should be doing something and just sort of minimizing that or getting rid of it, if at all possible. So finding dead time in a system, or having tools that find dead time in a system, to me is incredibly important and incredibly useful. What we actually did as part of just a mini project, we just looked at, okay, how can we instrument fork join so we can get some of the information out of the fork join framework that's going to allow us to get this type of information so we can do these calculations so we can actually get an idea as to what's going on, a better idea, right? So if we're talking about latency is the time from stimulus to result, dead time is just time where the task is stalled, doing nothing. Now remember at the beginning of the talk, if you were here for the beginning, which I assume you were, I talked about how the CPU guys managed to keep increasing the instruction retirement rates. They've been able to keep increasing the instruction retirement rates by finding places where the processor is stalled. In other words, it's looking at what's the latency picture inside the processor, where's the dead time, and they're using all kinds of tricks to say, okay, well, let's close the gap. Let's, instead of having the processor be stalled, let's have it actually doing something with the hope that it's actually really doing useful work. And when they start applying all of these tricks at the processor level, what you find is that there's a whole pile of gaps and lots of dead time in there that you can actually eliminate to basically make sure that instructions keep retiring at a faster and faster rate.
The biggest single example of that is hyperthreading then.
Well, I would say probably even a bigger example of that would be speculative execution,
Yeah,
right?
Yeah.
So, and out-of-order instruction processing. Well, out-of-order has been around for a long time, but the speculative execution is really nice. So if I have a branch which says if-else, I'm always going to execute the if while I'm evaluating the condition, right? And if the condition comes out that I should have executed the if block, that's a win. Right? And which is better than a hard stop, because that means I've advanced the process that much. Now, if I go to the else block, then of course I haven't lost anything, but I haven't won anything. So one of the obvious optimizations that we get is that we'll get code reordering so that if the else block is executed more than the if block, then we'll switch things around so that it's on the winning path.
Speculative execution usually just assumes that it's going to follow the code, will follow the path that it followed last time.
Right. So it's a bit off topic, but the point is that what it's doing is finding places where you'd be stalled and saying, let's fill that stall time in with useful work, and it's a really it's a technique that actually scales, well, it moves up the stack, so we use it all the time to find out what's going on. It's generally why I don't do much execution profiling. Execution profilers tell you what your application is doing. They generally don't tell you what your application isn't doing, and that picture is generally more important. Okay. Okay, so, right. So from the previous example, you just get like this simple algorithm, right? So if there's available hardware capacity, make the pool bigger, else add capacity, or tune to reduce the strength on the dependency. Right. So as I mentioned before, I said, okay, we want to improve fork join observability. So, you know, essentially, how do we do this? Well, when I started this, I figured, okay, no problem. We'll just look at the fork join code, and we'll just find the points of instrumentation, and it's all going to just magically work until you actually look at the fork join code. Has anyone actually looked at the fork join code here? Yes. I figured you would answer.
Right.
And Remy, I think...
He's the guy who wrote half of it.
He's the guy that wrote half of this.
He's responsible.
Okay, so please, Remy, do not take this personally. But after a week of looking at it, I really wanted to gouge my eyes out. It's extremely complex code. It's very, very difficult to understand. So really what I said, okay, so what are we going to do here? You went poking around for a while, and then you said, okay, fine, let's pick on this guy here. As it turns out, you can actually do some monitoring here. So what I'm going to do here is I'm just going to emit a signal out, and the collector of the signal is going to take the thread and some other bits of timing information, and it's going to store that someplace, and then when the task finally exits here, we'll just basically poke back out to this collection, and then we can take all of the results and accumulate it, and then what I actually did was expose this in an MX bean, right? So with this type of instrumentation, I could collect the service times, and I could collect the inter-arrival times. And those are the two primary pieces of data that I need in order to feed into the formulation so that I can get a very clear picture as to what's going on in this particular queue. I think this is the type of information you probably should collect from every single thread pool or work queue that you're actually using to understand what's going on. Okay. Okay. So let's see. I also did another benchmark where I just said, okay, what I'm going to do is I'm just going to create my own fork join pools here, and I'm going to submit the task to them, and then do the get afterwards. And what we ended up doing is just running these benchmarks under a bunch of different conditions just to see what was going to happen. Now, this workload is basically parsing data from a file. So you would expect that this would be I/O bound. And in fact, if you look at the CPU chart that we have here, right, you can see that the first chunk here is with 16 worker threads. The second chunk is with 8 worker threads. That's on my 8-core MacBook Pro here. And then you can see with 4 worker threads. Now, one thing to note here is the relative width of the CPU chart is approximately the runtime of the algorithm. Okay? So you can see that with 16 worker threads, performance is not really good, but not surprising, because look at all the kernel time in there as we're basically thrashing the I/O buffers. When we get to 8 worker threads, things settle down, and if you look at 4, things are, from an I/O perspective, are about the same, but I still have reduced the contention enough so that I'm getting slightly faster results here. So I mean, the obvious thing to do would be to look at this and say, okay, what does the picture look like with 2 threads? What does it look like with a single thread? To see what's going on. But it generally suggests that for this particular problem, I certainly don't want to paralyze. Right? I certainly don't want to apply a fork join in this case, right? So if you look at this particular chart here, sorry about how hard it is to read, but so in this case, smaller is better. right? So it's going to be response times for the particular workload. We have streaming on the left. We have going parallel in the middle. And what I did was I actually set up a condition where I just said, okay, let's stream it, but I'm just going to flood the system with a bunch of streamed jobs, so that's single-threaded. And then I said, okay, let's do the same technique, but instead of just streaming, let's go parallel. And as you can see, really, not surprisingly, the results of going parallel and then doing the same work, oops, flooded are approximately the same. But when I actually flood parallel, then you can see that the system starts performing very, very poorly. Right. So I think the conclusion we can take away from all of this, and there's a lot more that we could talk about the performance of the fork joint. For instance, like the one thing that I didn't really pick up on when we were creating the slides and looking at the data that I did pick up on when you were talking about it was really the importance of the allocation rates, right? So if you look at the object allocation rates for that particular problem, again, we'd have to profile to understand exactly where they're coming from. But I presume a lot of the allocation rate is actually an artifact of the fork join framework itself, right? Which means that if you go into low latency or environments that are sensitive to allocation rates, then you probably couldn't use a fork join at all, because those allocations rates are really off the charts in those type of environments. As a matter of fact, if you look at the allocation rate, it was bouncing between like 800 megs and
800
about
and 1,000, yeah.
Right, exactly. So that's really about the threshold where I can say that you can probably get some fairly significant performance improvements by just improving the memory efficiency of the application on its own. Right. So again, you look at a profiler to see what's going on. But if you found that a lot of that was just basically byte buffer and string manipulation inside the framework, then of course the obvious conclusion is that you'd have to probably abandon the framework in this case. So that's an aside. So again, when you decide to use parallel, I think you have to be very careful. You have to look at it and say, okay, do I have this environment all to myself, or do I have to share? Is the workload even suitable to support parallelism? Does it matter even at all, right? For some batch jobs, I wouldn't even worry about going through the complexity of parallelizing it. Well, I would maybe in Java 8 because the lambdas make it so easy. The
parallelizing batch jobs?
Yeah, exactly.
No, I think there may well be a case for that.
Well, I don't know. It's like, generally, it's like I run it and go off and do something else and come back, and who cares at that point?
Batch jobs can be pretty critical. They can be pretty time critical. I've come across those.
Right. So, and there's other cases where, like, if you look at trade, like handoff costs, right? So if you are parallelizing, then you have to get the data from one thread to another, which means that you need to put it in a common place, and then you need to do a signal, and there's often a context switch involved. And when you get into all of that activity, even that can be somewhat quite expensive, and you can get a lot of processing done in that case just by leaving it on the same thread and not switching to another thread, right? So I think where it's good is if you got the system yourself, you have a CPU-bound process. The workload can be split into independent parts. There doesn't need to be really any communication as you're doing any of the processing. And that's where this where this technique works. But if you have sharing, if you have mutability, if you have neighbors that you have to worry about, if you're not CPU bound, then you have to worry about that. And there's all of these concerns, I think, that you have to consider when you're starting to decide if you want to parallelize something or not.
Right.
I
think it's a really useful feature, but it's not the. Everybody got very excited, and I got very excited, I have to say, when I
oops.
Okay. I got very excited when I first came across it, because it does look great to be able to say parallel. You want access to this hardware, to all this hardware, and we're only going to get it through the JVM. So it looks like, and it is a great feature. They've done fantastic work to make the fault join framework, which is pretty hard to use in its raw form in Java 7. They've done great work to make it accessible. It's fantastic. Unfortunately, I mean, the downside is it's a relatively small set of use cases that it covers, and it's a lot of the time the ordinary things that we want to do, unfortunately, they aren't within that use case. For those things where it does work, it's brilliant. And you just have to learn, unfortunately, well, fortunately or unfortunately, it's real life. You just have to learn to distinguish those cases, those use cases that do fall within that area where it really works. I mean, I think the general remarks on the previous slide about sum it up, but they are. I mean, obviously they need expanding a lot, but this is the kind of thing that you're looking at. So I just grabbed Kirk's arm because the resources here are actually worth talking about a bit. This is Doug Lee's paper on guidance about when to go parallel. So it's actually it's pretty useful, and it takes in a lot of the things that we talked about in this talk. The next two are about things that are not quite, that we didn't cover in this talk so much. They got left in there, but I really like them. I didn't talk about micro benchmarking at all, but I'm a great believer. I'm not sure about Kirk, but I'm a great believer in benchmarking harnesses. And Java benchmarking harness is, I think, a micro benchmarking harness is a brilliant resource. And the second and the third resources there are from Alexei Shipalev, who's one of the main authors of it.
Number two, that's me too.
Oh, sorry, I beg your pardon. I apologise. So it's Kirk. It's Kirk. Oh, and by the way, somebody else.
No, and somebody else. Yeah. Right. Nobody important.
The third one is the resource for the Java micro benchmarking harness, and its documentation. It's not as much used as it should be, partly because the documentation, although it's very good, isn't very user friendly, I would say.
What for
the JMH?
Oh yeah,
we could do better. I have ideas about doing better.
Sure, certainly, probably somebody in the community could help Alexei produce better documentation of JMH. But I have to say, he's done an absolutely brilliant job of creating a framework that takes away a lot of the common problems that people have when they're micro benchmarking. You know, even some of the problems that we ran into when we were running some of the benchmarks. But
it's really huge.
At least we knew better to do things to avoid them.
Okay.
In the past.
And one last resource for learning about lambdas and streams. I can't resist recommending.
No, it's a good book actually.
Oh, right, really?
Yeah,
wow.
I said that. It really shows your thought process very well.
That's a good thing.
No, that's a good thing. That's a very good. So we have quite a bit of time left for questions. So we're happy to entertain questions. I'll repeat them here so that everyone can hear what the question is. The only comment I'll have is that as you leave the talk, please give us a good vote if you enjoyed it, and if you didn't, you don't have to vote.
Give us an honest vote. Yeah. give us an honest vote.
That's fine. Okay. So I know we had some people in the break come up and ask questions. Does anyone have any questions? Like Remy, do you have anything to say? No.
Perhaps just one thing.
Perhaps just one thing. Good. I poked the right bear.
There is just a common mistake, which is when you use a memory map file, using file channel.map.
Yes, the common mistake to use a.
You are not parsing characters anymore, but bytes.
Yes.
And usually people forget encoding at that point. So you have a faster program, but the program is wrong because it only works either in US or in Europe, but not.
Right. So,
right,
so
can I repeat the question? It's really aimed at me because it's my code that Remy's complaining
well,
about.
You can repeat the answer. Absolutely.
Right. So Remy's. It's not a question. It's a remark, and it's perfectly valid. As my code relies on a particular char set, the code that I showed you there. I assumed a particular line terminator. and I assumed that, and I didn't allow for the possibility that we might be using some other child set. And this is absolutely right. It was the code that was the code as rewritten or as considerably improved by Paul Sandoz that went into JDK9 copes with UTF-8 and one other child set, I can't remember which, and just gives up if it isn't one of those two.
My answer is better to this question. We just optimized the implementation to the text that we knew we were dealing with.
That's a Kirk answer. We knew it was going to be ASCII, so we didn't have any problem. But Remy is absolutely right in the sense that I shouldn't have shown you that code without saying, by the way, this code is not production standard. It's not robust, and that's absolutely true.
Absolutely. Any other questions?
Is Remy suggesting that because you're solving a different problem, some of the speed up in going to a map solution is due to the fact that you're solving a different problem? You don't have the overhead of the.
No. If you did have ASCII code, I mean, you can detect what kind of code, what child set you've got, and if you've got ASCII, then it'll work just as fast. I mean, what I've got will work. I think the objection is, if I've got this right, is that you can't. I've just assumed the child set that I'm working with, and that's not a reasonable assumption, because there are other countries out there besides America. I believe. I've heard.
We use a lot of parallel streams in the area where we are doing like REST calls or calls to databases. So actually not CPU bound, but things that we are waiting for something for some time.
Right. So repeat the question, Kirk.
Yeah. So you're using parallelism for conditions. Oh, that's a good idea. We can use the microphone for saying it. You can ask better than I can restate.
Okay. You mainly named CPU-bound code as a good candidate for parallelism. At least in the projects I work on, we mostly use parallel streams to access remote resources like a REST API or a database, where we don't have like CPU time, but more like waiting time or network time. So
you're using instead of using connection pools, then you're using fork join pools to do the work of a connection pool?
Well, we still have a collection pool, but we just parallelize the connection for REST service. So instead of just doing it in a series of calls, we just do it in parallel, because the overhead of the network time is just very high.
Okay, so and you're finding that actually is giving you better throughput then?
Yes, a lot.
Interesting. I'll have to think about that one. That's that's surprising.
Have you increased the size of the fork join pool to allow for the fact that many of your threads are asleep, are blocked on your remote calls?
Actually not. I think the performance gain is mostly that, like, connecting to remote resource takes so much overhead that doing it in parallel instead of sequentially, it speeds up a lot.
Yeah, my question was: are you using the default size of the?
Yes.
Right.
Yeah, this is quite interesting, because normally when you go down a network stack, you're going to run right into a lock, right? Which is why. So you run into a lock. If you parallelize across that lock, you're going to turn that lock's just going to get hotter. So it's quite surprising that this actually works. I really have to think about it. It's a surprising result. But then I was surprised that we got faster when we put more pressure on the I/O subsystem also.
Yeah. My expectation would have been that you would have needed to increase the size of the pool in order to compensate for the fact that that your threads are effectively sleeping a lot of the time. And I mean, the kind of the ideal situation for using for parallelization is that thread affinity. You know, a thread works on a single core all the time. That's not going to happen in your case, because of course your threads are going to be displaced for the very long period of the network transfer. So I think it is quite interesting that you're getting good performance, and it's a different model from the one that we normally think about.
Yeah, absolutely. It's quite creative, I would have to say. I wouldn't have thought of parallelizing that because I would have just assumed that performance would be worse in that case. Any other questions? Oh, we have one up over here. Here we are.
So you're basically recommending parallel for CPU-bound tasks. So what would you do if, in this case, you have an I/O-bound task?
Well, yeah. I mean, my sense is that that's not going to work as well. Mainly for the reason I just mentioned. I mean, your threads are going to be swapped out because they're going to when the I/O interrupt is raised, then they can't keep the core. So they're going to be swapped out, and you're going to have all the overheads of that. And I think you're going to need to. I would have said you're going to need to increase the size of the thread pool in order to compensate for the fact they're spending a lot of their time waiting on blocking I/O calls. But I mean, we're hearing that there's actually other models. We're hearing just now in the last question that there are other models in which this system can work that may actually give improved performance. So these recommendations. I mean, I think it's early days in terms of understanding how this stuff's going to work best. I mean, it takes some experience to see the scenarios in which an idiom as significant as parallel streams is going to work. So a recommendation, that would be the recommendation I'd have made, but it's provisional.
So a separate thread pool for these threads would be a better idea, or something like increasing automatically the thread pool if you see too many threads being blocked? Well, or something like that.
My thoughts on this have just been destroyed, so I really don't know. But in general, I would have agreed with Maurice. It's just that the thread is going to be blocked on an I/O channel, so it's not going to be doing anything useful. So if anything else comes in and you want useful work to be done, then you'd have to increase the size of the pool to compensate. That said, I'm not exactly sure the runtime conditions of what the gentleman down here mentioned. It could be such that the threads really aren't blocked on the I/O channel for a long time, that they're basically they get to read almost immediately. I mean, we've seen conditions like that happening, but generally when that happens, it puts a lot of stress on thread schedulers and other things that really now dampen performance in those conditions.
The idea of increasing of using another fork join pool is one that really runs into the objection that Kirk was talking about earlier about the tragedy of the commons. You can have different thread pools. I mean, and generally speaking, the recommendation is to have differently configured thread pools for different kinds of tasks.
Yeah, but
typically you want the workload for a thread pool to be pretty homogeneous in terms of, for example, its CPU I/O usage.
Yeah, but under those conditions, you still have to consider the overall global picture.
Yeah, I'm getting to that.
Yeah. Oh, sorry.
What you need to do is but the problem is that although that's generally good advice, in the case of the fork join pool, essentially what it assumes is that you have all this is what Kirk was talking about, and what he's desperate for me to shut up so as we can talk about it again, is that the fork join mechanism assumes that it's the only one using the cores. So multiple fork join pools will be in competition for a resource that is limited. And the other question, I don't think there's any way of dynamically resizing the fork join pool, is there? I don't think there is. Not currently.
No, there isn't.
Right. Okay, I shouted you down, Kirk.
No, that's fine. You've said everything.
Doesn't often happen.
Any other questions? Oh, right. Look who showed up. Oh yeah, so no, you just want us to repeat stuff. stuff. Right?
Actually, maybe I will.
Okay.
I actually wonder what it means for me as an application developer or me as a library developer now that we have this common pool there. Like, as an application developer, do I need to care about what libraries are doing, maybe? Because it's all a big jar hell.
Awesome. Okay, so as a library developer, a framework developer, I mean, what are you going to do?
Run and cry.
Run and cry, exactly. Okay. So after you finish running and crying...
Just expose the horror to the users. And say, I don't know what to do. Give me all the fork examples and tell me what to do, because I haven't a clue what your application does. Okay,
so you're suggesting, like, just dump the responsibility on the users. It's not a bad idea. It's okay. But let's look at what the JVM does, because the JVM faces this problem also, right? It's got to run on a whole host of different hardware environments and you know, different numbers of core, different socket configurations, all kinds of stuff is different, right? And so what do? When they start up, they probe the hardware. And they said, okay, what does the hardware environment look like? What are the reasonable decisions I can make so that I can fit into this particular hardware environment? Okay? And if I make the wrong decision, then what I'm going to do is I'm going to allow the user to configure me so that I can, so that it will override the wrong decision that I've just made. And I think that's a really reasonable approach, right? So you can make a best estimate for the different types of hardware platforms that you think that you're going to be deployed on, and then let the user override the decisions that you've made in the cases where they need to override the decisions. So, I mean, we see that with the fork join pool, right? It probes down, sees how many cores, says you get, you know, n-1 threads, and then says, if I got it wrong, here's how you can fix it.
Right, but that means that me as an app developer, effectively I need to look at what, like, more understanding of the libraries that I use, which is probably a good thing to do in general, so I'm not going to argue against that, but feels like it's easier to shoot our customers in the foot. And
well, my feeling is that in the good old days, when we're still, knee-high to grasshoppers, performance really didn't matter that much, and people were just interested in the gains they could gain, in gains they could achieve in developer productivity and things like that. So I mean, that was the big win, right? Nowadays, I think the game has completely changed, and we see that people now have to pay more attention to the hardware environments that they're deploying in, and what these environments actually look like, so that they can make better choices to help people, just basically have the best performance that they possibly can out of using your framework. So I think unfortunately, the hard work is now up to the framework developers. I mean, look at fork join, right? I mean, that's an incredibly complex piece of coding. It's like, not many application developers are going to pull that off, actually. Pretty much none are in a product environment. But they did the heavy lifting for us, and we get to take advantage of it, right? And as a library developer, that's your responsibility, is to do the heavy lifting. And part of the heavy lifting is understanding the environments that you're running in, so that you can be as adaptive as you possibly can to those environments. Oh.
Sorry. I just want to send one level deeper on it, if you like, or higher, sure, depending on which way you think about it. Back when we were like single core or really low core count,
yeah,
we would like write our code to do algorithmically what we wanted it to do, and then you'd give it to the JVM, and Hotspot would profile it, figure out the most efficient, find the hotspots in it, compile those, JIT them, run the code, run it fast. I didn't have to care about Hotspot, and we still don't tune Hotspot's JIT very often. Do you think we'll ever get to a world whereby I'll be able to, on a multi-core system, describe my problem in Java code, not care about the threading, ever, give it to Hotspot, and Hotspot says, I have this many cores, and this is the problem, this is what I do? Because sometimes I feel like, and it's easy to say this because I'm not a JVM developer, that we've given up, and we've said, we can't solve these problems in a heuristic, manage it properly, abstract the hardware way.
Okay. I'm not going to answer that question.
I'd actually say the opposite to that. I think that I completely disagree with you there. I think they've actually made a lot of progress. You are judging...
We have the right person to answer the question here.
So, yeah, okay.
But
I've started down. So
we'll put him on the spot.
I'll finish.
Keep going while I think of an answer.
I sounded stupid.
Sorry. Keep going while I think of an answer.
Okay, right. So let me say, I actually think that you're being unjust. The problems that were being solved before were much simpler. The hardware's got a lot more complicated, and the law of leaky abstractions operates here. So the increasing complexity is leaking upwards, and they're actually, I think they're fighting it pretty effectively. Yeah. I absolutely agree with your dream. It would be lovely to be able to say, yeah, it'll all be done automatically for me. But it's going to be the battlefront wavers backwards and forwards as the pressures on it. It fluctuate. So at the moment they're under a lot of pressure from the increasing abstraction, from the increasing complexity of the hardware, and that's pushing through to us becoming aware of it. But if you fell back to the simpler case where the hardware was not so complicated, and they were trying to solve much simpler problems, we've got fantastic control. I mean, it's a moving. What I'm trying to say is it's a moving situation. I think that the balance will come back more in our favour. I think we have to be kind of quite supportive of attempts in the infrastructure to manage this complexity and to present it to us in a usable way. I think on the whole we're still gaining.
Yeah. So sorry, can you pick up what you wanted me to talk about?
Well, he was saying that he wants Hotspot to basically make every single decision for him so that he just can write code and not have to worry about number of cores, number of, what the other libraries are doing, because Hotspot's going to magically make it all work. And it does a pretty good job of it so far.
Well, yeah, that's good. Okay, well, I'm Stuart Marks. I work in the JDK at Oracle. I'm mostly a libraries guy, not a VM guy, but I'll give my perspective on this. It's interesting. I mean, it's great that Hotspot is doing a good job for you guys, but I hear constant complaints about Hotspot. It's like, oh, I wrote this code, it's supposed to do this, but Hotspot did the wrong thing, so basically they have to go in and tweak things and so forth. And I think we're on the same path with the fork join libraries and the streams libraries as Hotspot was, but much earlier on it. So right now we don't even have the set of controls. All we have is the common fork join pool and a very blunt set of system properties for controlling the number of threads in it. And that's clearly not enough. And so actually we had an interesting exchange here before about, this talk has been about CPU bound jobs, but a few guys over here are using it for IO bound jobs.
Yeah, that was very interesting.
And actually I'll mention that like in Venkat's Venkat Subramaniam's streams talks, he actually uses I/O. He does like a remote call to Yahoo in a parallel stream, and basically he gets a huge speed up because he has a bunch of threads cover up the latency of going out over the internet. Mm-hmm. So it's not surprising at all, and I think that's what this gentleman over here is seeing. If he has a multi-core machine, it just spins up that number of threads and compresses out all that latency. So if all you're doing is things that have high latency, then if you throw those into the fork join pool, great. Now there's a big caveat there, which is if that's all you're doing. So if you fill up your fork join pool, common fork join pool with IO bound jobs, then the next complaint, and we've heard this already, is now my CPU bound jobs are all blocked by the IO bound jobs, even if the CPUs are idle. Okay, all right, next, and we had another suggestion back here. Oh, just put it in a separate fork join pool. There's no formal API for doing that. It's actually a coincidence of implementation that people have figured out that you can set up your jobs in the right way to run certain jobs in a different fork join pool. Okay, now what you're doing is you're reinventing a set of policies for saying, okay, well, I have this workload that has these characteristics and I want to tune a fork join pool, and you're writing this all in your program and you're compiling it into your application. Now if you run this on a different server with different network characteristics or different memory or different CPUs, you're going to have to change your program to tune it all again. So we're at a very immature state, and so what we need to do is capture this kind of activity, which is, okay, I have this workload with this characterization, I/O bound, CPU bound, requires a certain amount of memory. We don't know how to express that right now. There's no API for that, so we need to figure out how to do that, and then develop essentially a language that allows us to control that, or at least allows programmers to control that in a, I guess, in a more rigorous way, instead of hacking around with the system as it stands. But I think the hacking around with the system as it stands is necessary because we simply don't understand this enough.
Stu, do you think that's a programmer's job or an administrator's job?
Are you setting me up?
No, it's a real question. I have in my imagination some kind of administrative console which assigns threads or thread pools to particular cores. I think it's something you would do at runtime. I mean, it's just my idea. And when I've suggested that to Brian, for example, I've not had any resonance at all.
Yeah, no, I think it makes sense. So I don't know if it's a system administrator's job, but it's, you know, there's this whole DevOps idea, right? But it's an operational responsibility to allocate different workloads to different resources to different workloads. And so if you're a programmer writing a parallel algorithm, generally you don't sit down and say, I'm going to need 4 threads for this. And so the obvious thing is that people. Sorry, I'm reacting to something that wasn't said in this room yet, but the obvious thing that people see missing in the Streams API is, oh, how do I specify the number of threads? And that was deliberately omitted because programmers don't really need to say that, right? So if you say, gee, I want 4 threads, and then you run on a 12-core machine, then you're not, you know, you're going to be idle. Yeah.
Yeah, I mean, what you're saying is that developers generally just lack the information at development time to understand what the operational requirements are going to be. And what we find is that the operational people just lack the other skill sets and to make proper decisions in terms of like how to partition or resource sizing. You know. So you end up with like very poorly written administration manuals for different products. Sorry.
Oh, no problem. Anyway, I think we're all talking about the same thing here. So the way I'd phrase it is not, you know, lack of skills or responsibility, but it's rather separation of concerns, right? So are you writing a parallel algorithm? You want to write that algorithm in a way that is independent of the resources that have been provisioned for it. And then there's a resource provisioning task, which is, okay, given a workload with certain characteristics, what's the appropriate way to provision resources for it to make it go faster?
Just to answer to the first question, there is a good way to not take decision inside the library. You export your code as a stream and let the user use it in a parallel way or in a sequential way. That's the first thing. And you want some VM magic. There is a VM magic for that. It's coroutine, which is basically you can, when you do I/O, you can take the work and put it away from the thread. And I hope in the future, say Java 12, we will have coroutine.
How are we for time?
We've got 2.5 minutes left.
Okay, so we have time for a quick question. Yeah, okay, now you want it. I think you put your hand up.
Yeah, me again.
Yeah, you again. That's
so
fine.
basically discussing further what we talked about, could it be up to the programmer to characterize his workload, like saying, well, this task I know is going to be I/O bound because I'm doing I/O here. And then the hotspot could use that to optimize the workload in some way.
Yeah, but I would say that's generally a good idea, except for developers often get that assessment wrong, which is why I've been sort of very not so supportive of you know, hint annotations that, you know, we expect this, so we want, you know, this type of optimization to occur. Because generally what you find is that when you see that out in real production environments, you'll look at it and say, okay, what's going on here? Well, I mean, essentially all of the performance problems are a result of somebody making a bad assumption and optimizing the code in a certain direction. And if you're in a developer's pit, you're generally trying to make these decisions in a vacuum. You don't have all of the other necessary bits of information that you need to make an informed decision as to, you know, am I going? I mean, I just asked a simple question: what's faster, a bubble sort or a merge sort? Right? Well, it depends. Exactly. That's the answer, right? And if you're in a developer, you know, if you're sitting in your little cube, right, deciding do I write a merge sort or a bubble sort, how are you going to make that decision? Right? Well, basically, you're probably are, you know, if you're most developers, you can say, oh, merge sort, because that's cooler and it's got to be faster all the time because of whatever. But you know,
we're pretty much out of time.
Okay, we'll do one more and then.
Yeah. Thank you very much. Thank you very much for the questions.
Oh, hold on, we got one more. We'll let him ask his question.
Time's up.
Okay.
Well,
go for it.
Okay. We now only talked about the fork join to parallel stuff, but we also got the completable futures thing, and I got is the completable future by default using the same thread pool, the same common thread pool?
Yes.
And the second question is if for doing if you want to parallelize the networking calls, would you either use fork join or completable futures?
The answer to that question is, first of all, it does use the fork join pool, and secondly, you might well want to use the completable future instead of parallel streams if you had a complex series of dependent callbacks. That's really what it's good for. If you've got tasks that are dependent on others, then the completable future is right for that. Whereas actually, when tasks are interdependent, parallel streams don't work very well and sometimes don't work at all.